Welcome to APEC. It's November 29th, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on this call, along with everybody who was watching us on YouTube, as well as the many other live streaming channels that we're broadcasting to. I want to apologize to everybody for having to bump this conference. We did move it a little bit. I have been traveling. I visited Falcon Space. We did do the 5th APEC anniversary, and travel has definitely become more a part of things as I am visiting different labs and seeing what's going on there. It is very exciting, but again, sorry for moving things a little bit further out. We may have a couple of more changes in the future as well. I believe our next conference is December 20th, but don't quote me on that because I don't have calendar open. So today I am super excited. We have some really, really brilliant presentations coming up. Ioannis Xydous is going to present a detailed walkthrough on gravity, anti-gravity, and inertial control via electromagnetic means. Dr. Lucian Ionescu will be discussing the Ionescu-Alzofon Theory and the relationship between gravity and the strong nuclear force. And Jennifer Nielsen will be discussing topological torsion drive warp bubbles, magnetohydrodynamic fluid and field coherence applications of the Tuft theory. So there is a lot going on. This is pretty hardcore stuff, but we are also going to have presentations. We've got Drew. He is with us backstage. Mark Sokol may be along as well. You know, all of the usual suspects will be doing kind of updates on what is happening in the alt propulsion community. So again, if you have a moment, please subscribe to our channel. We're broadcasting on StreamYard primarily through the Alt Propulsion YouTube channel. If you haven't subscribed, please do so now. You can drop questions into the live chat feature. We don't always catch them as they scroll up, but we try, you know, and we will try and ask those to presenters depending on time constraints. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. I want to point out also that I have been adding story materials on a number of breakthrough propulsion topics. So that is something, I've got several of those up. I have more going up in the near future, and I'm really excited. I'm going to be putting up a new walkthrough on the Falcon Space Labs, as well as some testing. And again, Mark Sokol has been doing basically triplet state testing using a laser to pump his DNP assembly. So there is a lot going on here, and it is all really, really exciting. Pretty much everybody doing work in this area has big new breakthroughs that they can talk about. And so we're trying to just get those out there, you know, as rapidly as we can. So without further ado, I want to bring Ioannis Xydous in. Ioannis, hopefully I'm pronouncing that correctly, sir. Oops. Ioannis, your mic, actually, I'm just getting static on your mic. Did something change? Okay, there we go. Now I can sort of hear you a little bit. Okay. Do you want to try and say something? Okay. I cannot hear you. It's just static again. Do you have a yeah, I can hear you now. You're very faint. And there's definitely some static. Do you think it might be the headset connection? Do you have a different headset you could use or a different microphone? Okay, now the static.
No.
Now, okay, that's better.
No, it's okay.
Okay, can you hear me?
Yes, okay, yeah. Can you hear me too?
Yes. Yeah. Okay, now you're back. It's working. Okay. So we
Okay,
did
great.
just so folks know, we tested this before, so something changed, but computers, right? So let me bring up your presentation. So I should preface this for the audience saying you and I have been exchanging emails for like 25 years now. You were involved with the original lifter work way back in the day. And so you had reached out to me and said, hey, this is something that I'm still involved in, not lifters, but like propulsion in general. And you were like, I'd love to do a presentation of my work. And the thing I got excited about was I was like, okay, again, rewinding that clock 25 something years. I'm like, that's amazing. So it's an honor to finally meet you in the virtual flesh, so to speak, but also it's a true privilege to be able to have you present this. So let me hand things over to you. There is you're doing a screen share, so you can do the back and forward that way. And I will take myself out. I'll be here in the background if you need me.
Okay, great. So thanks for having me, Tim, and hello, everyone. I'm really excited to be here. It's my first time at age 50 attending a conference and meeting a like-minded group of hobbyists, experimenters, engineers, physicists, and enthusiasts who share an interest in extraordinary alternative propulsion energy technologies. Public speaking isn't my strongest skill, so I would like to apologize in advance, but let's see how it goes. Please follow the Zenodo link at the left bottom side of the slide if you would like to download the presentation itself and the walkthrough in case you are interested in. I'm originally from Greece and hold a degree in electronics. I worked for about 5 years as an electronic engineer in a small company in Athens, and later worked for about 17 years here in Switzerland as a software system test engineer, and right now I'm unfortunately unemployed. What has always inspired me, even since childhood, is a fascination with extraordinary technologies. That same curiosity still drives me today to explore them and work with them creatively. My journey began in a more systemic way when I bought my first PC around 1996. One of the first things I did was search online for patents, websites, online forums, and papers about unusual technologies in alternative propulsion and energy. By around 2000, I came across with Tim and others through Yahoo groups. I believe there was more interest in these topics during the 90s and the early 2000s, so I might be wrong. The theory I'm about to share starts with classical mechanics and expands to electromagnetism, gravity, and the consistent extension of special relativity. It also includes proposed experiments to test these ideas, as well as a demonstration I recorded back in 2009. Over the past 20 years and even more, I repeatedly explored, released, and later removed part of these ideas and a couple of experiments on personal websites and in papers, though at the time they were based on flawed concepts and mathematics. Still, my intuition kept telling me that there was something real behind it. The first slide shows the destination of this presentation, actually, but the real question is, how do we get there? So the best way is to start with something familiar, classical mechanics. So when we talk about propellant-less propulsion, we are really asking whether an isolated system, one not influenced by external forces, can gain momentum through internal means. And to separate the idea of a reactionless drive, which is impossible by definition, from a self-contained system, an isolated system. That distinction eventually showed me why the term reactionless was used through the years. In the drawing, two counter-rotating orbiting masses orbit along a cyclic path. The linear inertial action and reaction, according to Newton's third law, always cancel out. But when one mass moves clockwise, the rest of the system gains counterclockwise angular momentum. Here we speak not about linear momentum, but about angular momentum. When the other mass moves counterclockwise, the system gains clockwise. The system gains clockwise angular momentum. If both orbit symmetrically, the net angular inertial reaction cancels to zero. And that is, I believe, the reason about that is also may justify mathematically why it was called through the years as a reactionless drive. Here we speak that the angular reaction of the system is the net angular reaction of the system is goes to zero, but the inertial forces still exist, but they are balanced each other. They balance each other. That's the idea. As a result, the isolated system expected to be propelled only by inertial angular forces, since the angular inertial reaction is effectively zero, as we just mentioned. The expressions on this slide and on the next one are rigorously derived from classical mechanics. The full derivation is included in the first section of this work. Over the years, I tried many times, but without success, to find a rigorous online derivation that included angular components to show whether an isolated system could be propelled by internal means. Most derivations relied only on Newton's third law, using collinear forces as justification, and often misunderstood the challenge itself. As a result, they completely failed to account for the role of angular components. Yeah, okay, exactly. Yes, the main result of the derivation that it includes, oh, sorry, I think I went, no, it's number 3, no, it's okay. The main result of the derivation is that it includes tangential force or acceleration. If you ask most physicists or online forums about this, they will immediately respond that this is nonsense. If your model includes tangential acceleration or force, it means external forces are acting, so the system is not isolated. In my view, this is a misunderstanding in mainstream physics, though I could be also wrong. I'm not a physicist, I'm just an engineer, but yeah, I will explain later about this. From my perspective, an isolated system means that all power and force generation occur entirely within the system frame itself. Mainstream physics still resists this idea, largely because of how tangential acceleration is defined in textbooks. In the force expression, we see two terms that together account for the total action force. The first is the net centripetal force along the y-axis, a Bowden force that sustains the orbiting motion. The second is the net tangential force, shown here along the x-axis, which represents the real thrust force. Okay. So at first glance, this may seem incorrect. You may seen some YouTube videos that the propeller's propulsion appears on the y-axis. That needs to be discussed later if anyone is interested about it. That is partly true and partly not, as I will explain next. If angular velocity is constant, for example, the phase second derivative is zero, only the net centripetal force remains. The system simply oscillates along the y-axis around the center of mass, and in outer space it would never gain momentum. This is the case when we don't have tangential acceleration and only centripetal. The other illustration shows how real thrust can be modeled in terms of changes in system's inertia as long as the orbiting masses experience tangential acceleration. The system behaves as though it has reduced inertia, which in turn leads to acceleration of the system as a whole. Okay. Yes, exactly. So now that the inertial drive model has been introduced, let's consider how a mechanical version could work. In this setup, two orbiting masses move in parallel planes. This arrangement lets them orbit continuously with angular velocity, constant or varying, controlled by phase modulation. The outcome is sustained thrust in one direction. At first, standing waves may seem unrelated to a mechanical inertia drive, but if you look closer, each orbiting mass acts like a sinusoidal oscillation along the y-axis. Moving in opposite directions, they resemble two sine waves on the same line that combine into a standing wave. Yuri Nikolai Ivanov's work uses a simple trigonometric function and observes that the nodes can move along the x-axis, along with an interrupt mass when phase modulation is applied or when angular velocity or frequency changes. That observation is valid. However, such a system cannot produce acceleration of the whole system because the action is linear, and this is my view. This produces a collinear reaction throughout the rest of the system consistent with Newton's third law and the conservation of momentum. Consequently, a non-moving standing wave reflects the situation in the mechanical inertia drive where two orbiting masses move with constant angular velocity, producing no real thrust along the x-axis. When phase modulation or change in angular velocity is introduced, the standing wave gains acceleration and its nodes shift along the x-axis, mirroring the behavior of the mechanical inertial drive. Regarding the mathematical expression shown, this work derives tangential acceleration from the curved path followed by the orbiting masses. By contrast, Yuri Nikolai Ivanov's approach, though based on trigonometric functions, seems to assume curved paths only implicitly and derives his acceleration expression from the standing wave itself. The aim here is not to compare the two theories, but to acknowledge Ivanov's idea and to incorporate the concept of moving standing waves into our framework while explicitly introducing the requirement of curvature. As we will see in the following slides, we propose using moving standing waves as massless entities with confined energy that, when accelerated, exhibit inertial effects, an aspect not addressed in Ivanov's work. Furthermore, we will show that moving standing waves are central to both the acceleration and the shielding mechanisms of the inertial warp drive, which will be introduced at the end of this presentation. To understand how our model behaves, before attempting a real mechanical inertia drive, you can run simulations such as the one shown here. In this idealized case, the resulting thrust along the x-axis appears as a rectified waveform. It approaches zero, but never becomes negative. Compared to the net centripetal force, the tangential force is about 4.6 times greater. To reach this efficiency, angular velocity must cross zero and reverse, as shown by the Kian dust curve. In practice, I have never seen this done, likely because controlling large one-direction acceleration is difficult. Sustained thrust would require repeatedly reversing the orbit. Holding constant velocity, slowing to zero, then switching direction. That demands precise timing and not only. Another reason why such implementations do not exist is a common misconception, which will be addressed in the next two slides. I'm really awful in presentation, I know. Anyway, this simulation reflects, so we are on slide 6. This simulation reflects how most implementations should work, though in reality they appear to fail. To keep the orbiting masses moving in the same direction, one clockwise and other counterclockwise, with reversing their motion to achieve thrust in one direction, for example to the right, we introduce an angular velocity offset and adjust the amplitude of the phase modulation. These two parameters are tuned to maximize efficiency along the thrust axis, resulting in equal magnitudes for the net centripetal and tangential forces. As shown, the angular velocity nearly touches zero, but never becomes negative, ensuring that the orbiting directions remain unchanged. Okay. So here, this slide highlights the mistuning in mechanical inertial drives developed so far, in my view. In YouTube demonstration of these propellant systems with rotating masses, thrust is usually assumed along the y-axis, while I argue the true thrust axis should be the x-axis. The misunderstanding arises because experimenters lacked a guiding theoretical model relying only on classical mechanics and direct observation. To maximize thrust without reversing the orbiting masses, Current designs rely on two assumptions. Thrust is directed along the y-axis, while the x-axis contributions are cancelled with rollers constrained to the y-axis, or any small x-axis motion intentionally suppressed as it cannot be utilized. And increasing angular velocity enhances the centripetal force, which is often mistakenly referred to as centrifugal force. We know that the centripetal force reflects bound motion. So how do these devices seem to accelerate? They simply exploit surface friction, which breaks the action-reaction symmetry. Friction acts like a hysteresis that disrupts the principle. Secondly, you may have noticed that such devices accelerate briefly and then decelerate almost immediately, ending with only a small final speed that doesn't match the cycle's apparent acceleration. This effect is not caused by friction. Instead, it shows that the motion is bounded and the device is mistuned. Put simply, such devices will never achieve sustained acceleration in outer space, again, according to my view. Okay, test one, yes, simulation, yes. The test shown on this slide is a proposal, not exactly with extreme simulation values presented, but intended to introduce what we later call the benchmark velocity in the validation protocol. There is a validation protocol later in the slides that I'm going to present you. In practice, to qualify a device as a genuine mechanical inertia drive, it should be tested in a lubricated corridor that should achieve at least twice the velocity gain during the first cycle by the end of its translational motion along the corridor. I have always been interested in finding online simulations or calculations that show that what would be required for a mechanical inertia drive to overcome gravity, but I never came across any. Using the model I developed in my work, I decided to attempt the calculations myself by adjusting the frequency. As you see, I have set 15.91 Hz on simulation 2. And assuming the entire system has a mass of 1 kilogram, the results suggested that it could, in principle, float in mid-air. The challenge, however, lies in the mechanical integrity of the system. The orbiting masses would need to reach acceleration about 10 times greater than gravity, far beyond the current capabilities of mechanical actuators, which are typically limited to around 1 G. Although mechanical devices were never my main interest, I would encourage experimentalists or anyone curious to try building a small mechanical inertia drive with or without microcontroller-based control of angular velocity to test the claim about the true thrust axis. I don't suggest this is a way to validate my own work. I honestly don't mind. But if someone succeeds in replicating the claim, according to my view again, they will have in their hands a genuine model for all types of inertial drives, including electromagnetic versions with massless entities such as confined energy from standing waves or fields. Okay, we have now worked through 9 slides and arrived at the more serious material. The earlier slides were essential. They built the foundation for seeing how the model can be transformed and applied to electromagnetic devices. Here, the orbiting masses are replaced by standing waves that confine electromagnetic energy. As in the inertial drive model, we have both clockwise and counterclockwise guides in this case. I carry out some calculations to outline a relative feasible construction using 2 gigahertz propagating microwaves with a confined energy density about 10 joules per cubic meter. By applying an angular velocity shift equal to half of the base angular velocity, the system is expected to accelerate along the x-axis with a force of 6.7 Newton. For an isolated system with a mass of 1 kilogram, this corresponds to an acceleration of approximately 6.7 meters per second squared. And a rather unexpected result is that the corresponding energy density behaves like a massless object exhibiting inertia equivalent to 3.66 multiplied by 10 to the fourth power in kilograms, but it's massless, with an acceleration of about 91.5 micrometers per second squared. Multiplying these values gives a maximum thrust that is twice the 6.7 Newton. How can that be possible? These questions also troubled me while writing this paper. Initially, I thought the wave itself was responsible, but I now believe that was incorrect. What actually induces acceleration and produces inertial effects transferred to the rest of the system is not the wave itself, but its confined energy. Therefore, the induced inertial effects and acceleration must be calculated with respect to the confined energy. Along the same lines, this experimental setup was, believe it or not, partly and even accidentally recreated back in 2009. I will talk about that in the next slide, and also show you the recordings of the experiment itself. Instead of using toroidal waveguides, this experiment uses manganese, zinc, ferrite toroidal cores with their specification shown in the table. The standing wave that forms is mainly magnetic and interacts with the dipoles in the ferrite core. This creates what I would call a bulk magnetopolariton, but I don't expand at all, theoretically in the paper about this. As an observation, just I have put it in the paper. Basically, a mix of the field and dipole working together. The calculated frequency comes out to about 4.96 kilohertz, which matches closely with what's seen on the signal generator. However, this is outside the normal range of the material, since it is usually meant to work best between 20 and 200 kilohertz for power transformers and inductor applications. In other words, you cannot use 4.96 for power transformers and inductors, but you can use it to demonstrate such kind of effects, as I will show you later. Here again, we see that each bulk toroidal magnetopolariton has an equivalent electromagnetic mass of about 0.4 kilogram, which is quite close to twice the mass of one toroid. The one toroid, if you see the table, the mass of the toroid is 0.2 kilograms, which corresponds to an acceleration of 0.58 meters per second squared. Both values come directly from the energy density rather than from the wave parameters themselves. When we multiply these values together, we obtain again the maximum thrust. Okay. We now arrive at a slide that could represent either a paradigm shift. We speak about an EM inertial drive or primitive inertial warp drive, I would say, or a delusion. Maybe it's nothing. The background is this. Back in 2009, while studying the work of Professor Fran de Aquino, I attempted to measure the propagation velocity of the electromagnetic waves through a manganese zinc ferrite core using a very low power. My attention, however, drawn to the noise produced by magnetostriction, the slight expansion and contraction of the core. When I placed the ferrite core on the floor and applied more current without limiting the resistor, if I recall correctly, it suddenly moved with strong energetic motion in a diagonal direction with manually increasing frequency. The ferrite core's apparent self-propulsion was a shocking moment, unlike anything I had witnessed before, even though the first test in the YouTube video, as you are going to see, demonstrates a reaction that is about 5 to 10 times weaker. At that point, the material began to decline in its response. Fortunately, I managed to capture 3 different recordings When I shared them on the NASA spaceflight forum some years ago, they were skeptical. Some claimed it was a hoax using hidden magnets. Others suggested I was moving cables off camera, or that it was simply vibration interacting with the table. A few even said, suspend it and see if it moves, which I tried, but unsuccessfully. Everyone who commented focused only on the first experiment and overlooked the other two. The truth is that the material is extremely sensitive to current changes at frequencies below its allowed range, so it doesn't behave as one might expect. To see a proper response, one would need a fresh material rather than the degraded one I used. About 4 years ago, I shared both a theory covering various topics and the experiment on YouTube, but while I later removed the theory, I chose to keep the experiment available. As you are going to see in YouTube, is about 4 years online. So the first experiment you will see shows the ferrite core moving diagonally across the table's surface, driven by friction, a tangential force without changing the frequency. It's a special condition that was discovered accidentally, achieved by periodically increasing and decreasing the frequency until the ferrite appears to settle into a log state. So here we go. I hope it will work. Oh. Okay, the second experiment involved a Lego car with a ferrite core placed on its back, knowing that the force was tangential and that the material had already begun to degrade. I attempted amplitude modulation using a modulation signal of 100 millihertz. The goal was to illustrate a situation similar to trying to push a car while riding inside it. Oh, when I click, it stops maybe, I don't know why. Okay. It is very short anyway. And the third experiment focused on controllable rotation. Around 2009, or perhaps a year earlier, I came across the work of Yuri Nikolai Ivanov on rhythm dynamics. I wondered whether I could demonstrate controllable clockwise and counterclockwise acceleration of a standing wave along a curved ferrite path, thereby supporting Ivanov's claims about moving standing waves. At that time, I hadn't yet developed my own theory, and it was mostly influenced by Aquino's work, which seems to contradict my observations, particularly regarding the high frequencies compared to what one of his papers suggested. In this video, you can see that when I increase the frequency, the toroid rotates clockwise, and when I decrease it, it rotates counterclockwise. Oh, sorry. So you see here, it's 5.18 kilohertz, the signal generator. The calculated force is about 0.24 Newton. For a mass of 0. kilogram, the normal force is about 1.9 newtons. With a static friction coefficient of 0.3, the force required to overcome friction is 0.58 Newton, nearly 2.4 times greater than the calculated value. Even if we take the maximum force, possible force, which is about 0.488 Newton, it is still about 1.2 times smaller than the 0.58 Newton needed to overcome static friction. This suggests either that the static friction coefficient is less than 0.3 or that the actual force produced is greater than the calculated value. Although the deviation is relatively small, even under assumed ideal conditions, it's an encouraging result suggesting that the theory is on the right track. But again, you never know. For those interested in replicating the experiment, the material costs about $38 to $40. If you already have an acoustic amplifier rated at 40 watt RMS or higher, I use approximately 70 watt RMS for a 4 ohm load. You can wind 3 to 4 turns of wire around the ferrite to achieve an inductance of about 1 millihenry. For experimentation, it is advisable to include an inline resistor of roughly 4.7 ohm, and that can withstand about 150 watt, and to avoid using capacitors for resonance. The manganese zinc ferrite used here is not suitable for practical applications, but serves well for demonstration. I would welcome feedback from anyone who attempts to replicate the experiment. With the right laboratory setup, other ferrites or even iron cores could be tested. Using a pair of such materials might reproduce the inertial drive model electromagnetically and suggest a promising propulsion concept for space, at least in its early stages. As a side note, it remains unclear whether anchoring the rotating core, iron or ferrite, would transfer the generated momentum through the accelerating standing wave to the rest of the system. This aspect of the theory hasn't yet been experimentally verified, although the second experiment with the Lego car appears to support it. Okay, here we have the protocol. The findings of this theory allow us to establish a validation protocol to determine whether a candidate device qualifies as a genuine inertial drive. We don't need to cover every detail here. What matters is the main criterion. The device must produce real thrust perpendicular to the excitation, and if the device is treated as a black box, it should demonstrate at least twice the initial acquired speed by the end of a long lubricated corridor. As you may understand, and as I said, earlier, the most mechanical, at least the most mechanical, they do not comply with this validation protocol, which is a very good, I think we could discuss it, later or even offline with anyone, interested about it. So we go on this next slide. Okay. I included a special section as an attempt, not a full examination of Podkletnov's gravity shielding experiment. My goal was to see whether I could describe the experiment using the framework I have developed so far, applying certain known parameters and making a few assumptions. In the experimental setup, the rotating superconductor gradually decreases its angular velocity according to Podkletnov's parameter values. Under those conditions, a nearby 1 kilogram mass showed a maximum weight reduction of about 2%. I used 2.4% in my analysis. What happens is this. A pulse generates circumferential supercurrents, and in the superconducting state, the Meissner effect expels the magnetic field from the superconductor, creating a poloidal-like topology as illustrated. The rotating poloidal magnetic field together with the induced motional electric field resembles a mechanical electromagnetic standing wave. while the disk undergoes controlled deceleration, the mechanical electromagnetic standing wave accelerates in the opposite direction, transferring momentum or an inertial field into the surroundings through the accelerating confined energy. Once again, we see that the confined energy behaves as if it has an effective inertia of about 3.83 milligrams, with a corresponding acceleration of roughly 2.05 multiplied by 10 to the second power meters per second square. These counterintuitive values clearly require further investigation and control experiments to confirm their validity. With the assumed reduction in weight and the calculated thrust, the energy density comes out to about 2.9 joules per cubic meter. After running the numbers, it looks mechanically feasible to achieve a deceleration lasting around 39.5 seconds. During that time, the system's weight would drop to about 2.4 of its original value. Another unresolved issue is how the setup generates an upward thrust or inertial field once the energy is confined around the circumference. One possible explanation is that the vortex forms when poloidal magnetic field lines couple with azimuthal motion, though the exact mechanism is unclear. Podkletnov suggested this effect might be explained by vortex theory, but that's not something I cover in my work. Up to this point, we have seen that confined energy with standing waves, when accelerated or decelerated, can transfer momentum to its surrounding. Neutral mass may interact with this momentum, resulting in either in acceleration or in apparent reduction of weight, depending on the direction of the force produced by the confined energy. This raises an important question: does the translation of confined energy exhibit gravitational-like or inertial-like field properties? In this section, I present what may be the simplest derivation of the coupling between electromagnetism, gravity, and inertia. By equating the thrust force derived from electromagnetic parameters with an equivalent gravitational or inertial thrust force, or by equating the corresponding energy densities, we can establish a theoretical link: electricity with gravity and magnetism with inertia by analogy. Setting the gravitational permittivity equal to 4 pi multiplied by the gravitational constant, we can then derive its counterpart, the inertial permeability, in analogy with the magnetic permeability of electromagnetism in Maxwell theory. Furthermore, by defining electromagnetic mass and integrating it with the new expressions dg and di, these two have Newton per kilogram or meter per second square as the units of these two expressions. We arrive at the concept of the electrons or positrons' effective massless electromagnetic mass. Remarkably, when this electromagnetic mass is divided by Planck's mass and squared as a ratio, it unexpectedly yields the fine structure constant. I'm very awful. I think it was a bad idea to make a video. Anyway, I couldn't leave this out of the presentation since it directly relates to the link between electromagnetism and gravity. The link at the bottom, titled Hidden Geometries in Maxwell's Equations and the Force Flux Route to Unified Static Fields, builds on a work I developed a few months ago following an earlier paper titled Classic Unification of Electromagnetism and Gravity. In fact, the paper extending Maxwell's equations should have carried the unification title, but the idea only emerged later. A physics journal reviewer of the first paper rejected it, saying he saw no connection between my proposal and Maxwell's equations, since I was discussing gravitational charges using the concept of a general gravitational potential. That comment made me think, why hadn't I considered Maxwell's equations from the start? So I began writing the new paper, and during the process, I discovered expression inspired by Gauss's field flux, the first of the for Maxwell equations. In my view, if Maxwell, around 1860, had introduced a force flux law, it wouldn't have described a new field, but would have allowed him to replace electromagnetic constants such as electric permittivity and electric charge with gravitational permittivity and gravitational charge. The result would be the same Coulomb force, but now expressed in terms of gravitational parameters. In that speculative framework, Maxwell could have uncovered a link between electromagnetism and gravity, even though no experiments at the time were available to confirm such a connection. This work suggests it calculates the existence of 3 additional emergent charges associated with the electron itself. How can that be, you may ask, given that the electron is treated as a single purely electric entity? Consider a spinning electrically charged metallic spherical surface. The motion of the static charges generates azimuthal currents, which in turn produce a magnetic field. That magnetic field can be understood as an emergent magnetic dipole charge, which disappears once the rotation stops. By analogy, gravitational and inertial charges could also arise as emergent entities created through the acceleration or deceleration of a spinning electrically charged metallic sphere. Ultimately, this work derives through a Maxwellian approach the link between electromagnetism and gravity, yielding the same electrogravity and magnetoinertia expressions shown earlier. In simple terms, changing the polarity or direction of electric or magnetic field can create a counter effect, an anti-gravity response that opposes Earth's field lines, producing a locally weaker gravity zone or even reversing them. By integrating a Lorentz-like field into Maxwell's equations and combining it with the force flux law, we obtain an expression resembling the Lorentz force, but now describing the unified field, for example, of the electron. In practice, if we select electromagnetic constants, we recover the electron's total electromagnetic field. If instead we select the gravitoinertial constants, we obtain its total gravitoinertial field. Here, the gravitational field is expressed in units of kilogram per meter per meter. That means, if you in place of volt, we have kilograms per meter, the gravitational field, the units. While the gravitational displacement field is measured in meters per second squared, as illustrated in the plot. At a distance of 0.12 nanometer, the electric field is approximately minus 1.13 multiplied by 10 to the 11th power volt per meter, while the gravitational displacement at the same distance is minus 9.81 meters per second square, equivalent to minus 1 g. I chose to plot gravitational displacement rather than the gravitational field itself, since its units and magnitude is more familiar and directly relatable to our everyday experience of Earth's gravity. Something I have written in an older paper that I didn't include or even removed in any of the papers I have released so far, and this is because a reviewer was disagreeing with my proceedings and said that it was wrong and disregards the Casimir force. I believe the second part of the electron total field seems to have to do with the Casimir force. Thus, quantum fluctuations shouldn't have any relations with the force in general, again, according to my view. In 2004, physicist B. V. Ivanov, it's not the same Ivanov as in the beginning. This Ivanov is from the Institute for Nuclear Research and Nuclear Energy in Bulgaria, published a paper on the link between electromagnetism and gravity, which he called root gravity. His work produced the same formulas using natural rather than SI units that predict the exact electric field and magnetic induction needed to generate 1G. In the discussion section of his paper, Ivanov points out that the connection between electromagnetism and gravity could have been identified many times, 8 times, in fact, over the past 80 years, counting from 2004. His approach relies on advanced mathematics such as tensors, general relativity, and WMP, well, Mayumdar, Papapetru, space-time solutions, while my proposal uses only high school level math applied to classical electrodynamics and Maxwell's equations. Okay, in this work, I include a section on the Alcubierre warp drive, not to introduce a new metric, which I'm not capable of doing, but to examine the energy requirements using specific values and later compare them with my proposed inertial warp drive concept. For this purpose, I use an energy scaling estimate expression. It is dimensionally correct, though not an exact solution, and I expect to remain within an order of magnitude of the true result. Importantly, it doesn't assume a specific bubble geometry. As shown for the chosen parameter values and a bubble thickness of 1 meter, the energy requirements are enormous. As a teaser, I suggest the possibility of using electromagnetic fields to create massless inertial fields that could achieve the same goal without distorting space-time. However, as we will see in the following slides, the electromagnetic energy we speak about, the confined energy associated with massless electromagnetic mass, cannot be equated to rest energy as described by Einstein's famous relation mc square, which reflects the conversion of annihilated mass into energy. And finally, we arrive at the ultimate destination, the inertial warp drive. In this concept, an inertial shielding effect is incorporated into Minkowski metric, the so-called flat space-time, through the reduction of the local propagation rate. This effect arises from a pair of counter-propagating accelerating standing waves, which essentially isolate the system's inertia from the rest of the universe. This is an assumption, of course. The velocity of the system is determined by the net tangential velocity of the standing waves. In this framework, the system's mass is not its bare mass, but an electromagnetic mass, similar to the magnetopolariton concept. Put differently, the system's mass doesn't exhibit ordinary inertial properties. Instead, it reflects an electromagnetic inertia that can be controlled through time-varying phase modulation. As a result, the system energy is no longer governed by Einstein's relation mc square. The concept of the inertial warp drive requires a broadening of special relativity, which I term inertial relativity. In this framework, special relativity becomes a subset that describes relativistic motion driven by external forces. The 3 plots illustrate how relativistic inertia, velocity, and momentum behave in comparison with both the broadened framework and classical special relativity. In inertial relativity, inertial can reach a minimum of 0, producing a transparency effect where the system becomes essentially undetectable. Velocity, on the other hand, may cross and even exceed the speed of light barrier, since the final velocity depends on the amount of confined energy available per cycle. Finally, momentum in inertial relativity rises to a maximum value before decreasing back down to 0. It's worth noting that when we set ns equal to 1 in the new relativistic inertia expression from inertial relativity, we recover the formulation of Dr. Carezani, an Argentinian physicist who introduced autodynamics around 1951. Although Carezani didn't invoke inertial shielding, his approach of reducing inertial frames leads to an outcome that coincides with the inertial frame aligning with the wave field. Another important observation is that all tachyon or superluminal propagation theories that treat C as a strict lower bound. In both special relativity and these theories, there is a discontinuity at the velocity equal to C. In contrast, inertial relativity and Karzani's relativistic expression do not exhibit such a discontinuity. A possible technical approach, though it requires special materials, is the use of surface waves similar to the ground waves employed in long wave radio communication, which follow the curvature of the Earth. In this case, the inertial warp drive would operate with surface standing waves, most of their confined energy lying outside the spherical shell, yet still capable of accelerating by following the curvature of, for example, of a spaceship's hull. When we apply the same parameter values used for the Alcubierre warp drive to the inertial warp drive, treating the bubble dimensions as a spherical shell of equal radius, we uncover a working frequency of 238.8 kilohertz, which lies in the long wave radio spectrum. Because standing waves can never be perfectly confined, some energy will leak into outer space. This leakage could be used to identify the propulsion or shielding frequency, or even estimate a spaceship's dimensions with a custom software-defined radio receiver. I added this. What I'm going to address is something that I don't include in my work. I put it here, as a teaser for those who would like to explore this as a project. So the idea is the following. If extraterrestrial spaceships use this principle as the inertial warp drive, their propulsion and size might be detectable, though, as with any radio receiver, distance and sensitivity remain central. By directly converting the received signal without demodulation into digital data, a deeper investigation becomes possible. Based on the findings of this work, the inertial warp drive is expected to operate by changing the angular velocity of standing waves. This creates a frequency shift similar to FM modulation, but without a carrier. While such carrier-less FM isn't possible in a radio broadcasting, it's comparable to SSB single-sideband AM, where AM modulation without a carrier is feasible. For spaceship objects with radii between 1 and 1,000 meters, the working frequency of a single standing wave for propulsion or shielding is expected to fall between 80 kilohertz and 80 megahertz as carrier-less FM modulated signal. What I found extremely interesting is that the terrestrial radio broadcasting band from 80 kilohertz to 80 megahertz uses AM modulation, not FM. So if we capture signals in this band and convert them directly into digital form without first demodulating, we can store this data on a PC. Then by applying software-based digital signal processing, we could filter out the AM content and scan for frequency shifts. Virtual carrier through the processing software, we could even demodulate carrierless FM signals, opening the way to detect otherwise hidden modulation patterns. It would resemble hunting for ghost-like SSB FM signals, which in reality, they do not exist. But if, these spaceships use this principle as the inertial warp drive, there is a good chance that we could probably, receive such kinds of signals. So besides the frequency shift, both shielding and speed are proportional to the confined energy. This means the carrier-less FM signal could reveal speeds only up to the speed of light, but not beyond. For the same frequency, the final velocity may fall below or appear above light speed, as shown in the work through the NS energy factor. I imagine such a detection setup could work like a non-rotating passive radar antenna that only receives signals, like a typical radio. For now, this remains speculative, but as I wrote this presentation, I became so absorbed in the idea that it struck me as an exciting and fully feasible exploration project, combining RF electronics, ADC conversion, PC-based signal processing software, and machine learning algorithms for automatic detection. It would be a thrilling moment if at an upcoming APEC conference, someone presented the equipment as also genuine, not faked recordings of signals that might be coming from potential extraterrestrial spaceship sources. Such a discovery could mark a new chapter for the conference itself. So returning back to the presentation, the expressions linking gravity and inertia with electromagnetism allows us to calculate the required energy density. From this, we can determine the energy needed for a spaceship of given dimensions to accelerate almost instantaneously within 4.18 microseconds from rest to 10 times the speed of light. By considering the electromagnetic volume through which the standing waves propagate, we arrive at an energy requirement that is many orders of magnitude lower than the estimate derived from the Alcubierre warp drive. The inertial warp drive section concludes with an attempt to reconcile Alcubierre's energy requirements with inertial cell dynamics. Put simply, the question is, what must change in the Alcubierre warp drive model for it to become an inertial warp drive? Instead of warping or distorting space-time itself, the inertial warp drive applies a warping or bending of system's inertial response, achieved by influencing the local propagation rate through electromagnetic means. By multiplying and dividing with 4 pi and the square of the wave period, we can transform the energy requirements of the Alcubierre energy estimate. Two adaptations make this possible. First, we define the velocity to time ratio as the tangential velocity of a single standing wave rather than the pair. Second, we replace the thickness with the product of the speed of light and the wave period. This substitution allows to be re-expressed as an electromagnetic volume. While calculating the equivalent electric field strength associated with the required energy density, we find that it exceeds the Schwinger limit, the threshold at which the vacuum becomes nonlinear. It begins producing electron-positron pairs, according to quantum electrodynamics. This implies a natural limit to acceleration, roughly one-third the speed of light per second. That is equivalent to 11.6 million times Earth's gravitational acceleration. In addition, this poses an energy density limit for confined energy that must not exceed approximately 1.5 multiplied by 10 to 25th power joules per cubic meter. A big unanswered question is how the spaceship keeps moving once phase modulation for acceleration stops. At constant speed, the inertial shielding, both for propulsion and for protecting the crew, switches off because it only works during acceleration. This means separate shielding would be needed for propulsion and for inertial, as also adaptable phase waveform control based on the current acceleration and velocity of the spaceship. Here you will find the papers I have released so far, brought to a satisfactory conclusion, and which I do not plan to remove in the future. The last 3 were rejected by physics journals, and in the coming days I plan to submit the new paper titled Engineering the Leap to Inertial Warp Drives to the MDPI Aerospace Journal Special Issue on Breakthrough Propulsion for Spacecraft. This issue is guest edited by Martin Tagmar of Dresden University of Technology and Les Johnson of NASA's Spaceflight Center, with a submission deadline of June 30th, 2026. However, publishing is costly, and based on my experience and the many rejections I have already received the last 10 years, I doubt this paper will be accepted. Furthermore, I recommend a few resources that I think should be part of everyone's toolkit. I strongly suggest downloading the JLN Labs website for offline use. It's one of the richest collections of open experiments in alternative energy and propulsion technologies, and it's also one of the oldest sites on the web, dating back in 1997. You can also find me listed in the System G section as John Xydous, dating back to around 2003, sharing my analysis about the System G. It is an anti-gravity device from Professor Aquino. You can use Sciotech web copy or any similar tool to download the entire website while it's still online. I have already done this myself. I also recommend the work of Professor Aquino. Nearly all of his papers are experimental proposals in alternative energy and propulsion, and they can be a great source of inspiration both for those already working in the field and for new enthusiasts. Thank you for your attention.
Ioannis, that's amazing. That is amazing. You were selling yourself short. You're like, I'm not a good presenter. You are an amazing presenter. That was amazing, man. Thank you. Thank you so much. Well, let me bring the guys in here. Let me bring the gang in. I'm going to take down the thing.
Thank you very much. Thank you.
Guys, put your hands together and give Mr. Ioannis Xydous a giant applause. A giant applause.
Thank you. Thank you very much. Thank you.
And we had our share of bugs along the way. We had some mic noise. We got that solved. The other thing, and folks mentioned this in chat. So
can you hear me now? Now can you hear me?
Yeah, I can hear you. StreamYard just did an update to their platform where basically it broadcasts in phone view and it broadcasts in web view. And it defaulted to doing both. And so some people got on that phone view stream. So next conference that I set up, because we're live right now, the next one I set up, I'm just going to disable that and it will only be web view. It will only be the landscape. So, our share of bumps along the road, but that is APEC. Nothing ever goes exactly according to plan. And this is an amazing presentation. And then another thing I should quickly mention is, Ioannis, I chatted you. What I want to do is create a story and a breakout video on this and put those on the Alt Propulsion website to help people understand it. And I want to do the same thing for Lucian Ionescu's presentation, which is coming up in just a minute. So thank you again, sir. Thank you so much.
Yeah, that would be great. That would be great.
Wonderful. Okay, well, so we're actually 10 minutes over. So what I'm going to do is I'm going to take everybody out. But again, one more time, let's put our hands together. Mr. Ioannis Xydous, an amazing walkthrough, and that gives a lot of people material to think of. People were actually pinging me in chat during it saying, I want to read this. I want to get more information out of this. So you're definitely going to have some people going through this. Thank you again, sir.
Thank you.
Okay. Sorry about that. So yeah, we're running a little bit over. Lucian, let me apologize to you. I'm really excited. We're doing really well. So Lucian Ionescu, you are, if I understand correctly, a professor of mathematics, right?
Yes, correct.
But I know you from countless Tesla Tech conferences, and you have been a member of that community as well as an independent researcher breaking new ground in physics and mathematics and gravity forever. I mean, going back years. And so it is truly an honor to have you present at APEC.
Thank you so much.
What I want to do is I'm going to put your slideshow up. And again, both yourself and Ioannis are this is the meat and potatoes of really what APEC is about. So I want to do breakout presentations for this as well.
Sure. So how do I advance the slides? Can I do that?
If you put your mouse over it, there should be a slide and it'll show a little drop down that'll let you select. It also has back and forward buttons. Do you see those?
Oh, yes. Okay.
Okay. Wonderful. Right. So let me take myself out and take it away, sir. And thank you yet again.
All right. Thank you so much. So I assume I am on. Then thank you, Tim, for the invitation to present in APEC. And I wasn't sure, I must say, how this works, if it's just a stream presentation or discussions, and you as a mediator maybe have some questions. So my slides are more like a skeleton of the topics I wanted to discuss. And I have, of course, several other presentations that I can pull up and share screen and refer to those. So we might want to do that later on. So I thought that it's about time to step back and have like a synoptic opinion or statement of what is the status of gravity theory and gravity control technology. So I was planning to refer rather to some advancements which are not as well known by the various audiences regarding gravity research, and then maybe a little bit unexpected to start engage the audience, the readers, the viewers, not necessarily those online right now, but those who might read these slides later on to help. And for the typos here and there, it's very important to get away from the trap of doing research and development without looking what others are doing. And then many independent researchers would pull in different directions, and we won't ensure a coherent advance in this area. But about this a little bit more later. And still, actually, in connection with this, there is a need to help mainstream science. Physics is somewhat stuck in the 1970s version of the Standard Model, and it's not easy to, first of all, it's not possible to include the various alternative theories as being too separate from the Standard Model. So we have to start looking at how to connect with the Standard Model and how to glue or rather integrate our theoretical developments in at least in the language of the Standard Model. And last part, help with the gravity control technology. The point is, the stage by now shifted in the area of developing the technology of gravity control. But that means solid state physics, means two-dimensional materials, engineering, and those are areas where those who started the theories and understood the experiments and so on do not have an expertise. So it's clear that by now we need to form teams to develop such a complex, extensive subject. So gravity research, and at this point I might say the real breakthroughs happened with Frederick Alzofon in the 1980s, and essentially has almost nothing to do with general relativity and the physics, physics of gravity prior to that. Also because this breakthrough developed or engaged the research in the area of elementary particle physics. Therefore, in the turf, if you want, of the Standard Model. Now, the Standard Model, it's an amazing achievement of physics, theory, technology, teamwork, and all that. But they systematically disregard gravity as saying, well, it's too weak to be measured, therefore we are not studying it. On one hand. On the other hand, that's explained so beautifully by Einstein's general relativity. Therefore, it's applied to cosmology, to astronomy, and we won't get into that area. It's their turf. We do the lab and particle accelerator developments. But this is a very important point to emphasize. Pause a little bit if you want. Science is very much fragmented because of the way it was developed by individual researchers, by individual types of experiments which focus on some particular type of phenomena. And then the need of unification is obvious, and progress goes in that direction. One of the fundamental of the best examples is unifying, say, electricity and magnetism, Faraday, Maxwell, and so on. On the other hand, back to standard models, one in elementary particle physics and the other one in cosmology, because I would rather think of general relativity as a standard model in cosmology. Those two are very much separated, and there is a movement, so-called quantizing general relativity. But that's essentially a wrong way to try to save, say, general relativity. And there are, of course, there are many things to be said about that, but maybe not right now. So again, separation led to this dichotomy. Elementary particles, we have the standard model, and then cosmology, we have general relativity. Back to the breakthrough. Frederick Alzofon, who, first of all, was a professional physicist working in a very big laboratory with particle physics, with nuclear physics, with anyway the analog of Fermi lab, but I don't remember exactly which lab he was working on at that time in the 60s. Had an intuition that gravity has to do somehow with the polarization of what he thought at that time is some vacuum fluctuations, positron electron pairs, and the free energy type of thinking. He then tried to get a better understanding. I mean, he also knew about UFOs and so on. Anyway, the story is really exciting, and I encourage you to read the book written by his son, David Alzafon. He has two sons, David and Daniel, another physicist. Anyway, so to read his book, or at least this part of that book, documenting Frederick's Alzafon work, called Gravity Control with Today's Technology. I think I'm close to what the real title is. To learn more about the history behind his breakthrough. At this point, I would like to make a correction. So he advanced an effective theory for gravity, which is not really what's going on. But more importantly, he performed the experiments which verified that by dynamical nuclear orientation of the nuclear spin, one can modify the weight of a body in Earth's gravitational field. Now, that's the experimental part which demonstrates that the core idea is correct, and that gravity is really a byproduct of nuclear structure, nuclear force, and belongs to the realm of elementary particle physics as a theory. Later on in the 2000 and something, let's say 5, 10, I started to understand clearly that the quark structure with their fractional electric charge obviously is the candidate for a perturbation of the electrical interaction between two particles, like neutrons, for instance. Two neutrons, total charge 0, viewed in this way, they're not supposed to attract each other electrically. But when you consider those fractional charges, then it's almost clear that changing the spin direction of each might affect how the three fractional charges of quarks of one neutron will interact with the three others of the other neutron. So I started to write and explain this and coined that gravity is just the polarization of nuclear spin. And then after setting foundations of gravity based on the standard model of quark structure, I came across Alzafon's work through David Alzafon's book, confirming clearly that this is indeed the case through his experiments. That's why I decided to call this the Alzafon Ionescu theory. And you can find the articles where I explain it in the Vixra archive. There are links contained in this slide presentation, and I will not go over like a tutorial of the corresponding theory in today with my presentation. Also, compared to the previous presentation, beautiful presentation and with a lot of mathematics, it's not, you don't need to understand mathematics to nor general relativity to understand these basic ideas. At the conceptual level, that gravity is a consequence or a byproduct of a polarization of nuclear spin. And then just start looking at the experimental proof of this. And this is exactly what Alzafon did. And at this stage, I would also emphasize this theory. It's so elementary and so natural that several others came with this connection between gravity and nuclear force. One of them, which I learned recently about, is Kai Darmos, who has a compilation of experiments demonstrating that gravitational constant, the so-called big G, is material dependent. And more than that, by studying the corresponding dependency, one can almost immediately come up with a linear equation, proportionality between gravitational force or gravitational constant and the number of nucleons of the corresponding element. Again, this is, I would say, at the level of a high school lab experiment. Once you have the data and you analyze it, you can come with like a Hooke's law or proportionality between G and the number of nucleons of the corresponding chemical element. And maybe I should show this at this point. The picture is taken from the interview of Sky Demos took by Robert Sheldrake, or Rupert Sheldrake. I encourage you to watch that interview and get all the information behind what I mentioned earlier in brief. So back to the fact that the theory of gravity is really simple once you understand that there is a quark model behind it, that they have fractional electric charges, and then that electric force is really just the divergence part, or let's say it's the part of the force of a field which has a divergence. So this is explained in Sky Darmos' work. He has a so-called complete guide to quantum gravity. Now, it's by far not complete, but well, we all tend to exaggerate a little bit. But what I also avoid is to call such a theory quantum gravity, because the term is very much reserved to another type of theories which try to quantize general relativity. And I'll come back to this later on. So there is no, the main point here is there is no need to quantize general relativity, a theory that was written more than 100 years ago with a language which is 200 years old, differential geometry, Riemannian geometry, and not first of all, use what we already have, the standard model. And also, when writing a theory, one should write it in quantum framework from the beginning. No more continuous space-time and the old languages of differential geometry and so on. So again, as a quick recap, Frederick Alzofon effective theory based on quantum fluctuations of the vacuum is an effective theory, but it's not the true origin of gravity. On the other hand, the true origin of gravity anybody can understand once learning about the quark structure, which is usually neglected by any, let's say, high school level introduction into physics and matter. And they talk about electrons, protons, nucleus, atoms, and they stop at that level without giving like another one or two lectures that these protons and neutrons do have a structure, the quark structure. So at this point, it's clear that we need also to advocate some simple changes, updates in the educational system. So enough of that for now. Then again, about research on gravity, there is a plethora of peer-reviewed articles relating gravity and nuclear force. So the researchers are aware of that. How many articles? I would say more than hundreds. But you need to use an AI to do the search for you. And more importantly, you have to be open to learn in parallel to developing your own theory. Then there are many peer-reviewed articles studying nuclear spin-to-spin interactions, which are part of the Standard Model, part of the Lagrangian of the Standard Model. So this term is clearly pointing towards an explanation of gravity in terms of the nuclear force. But these peer-reviewed articles are written by physicists who work using the Standard Model, which again ignores ab initio gravity is not having to do anything with fundamental forces. So at this stage, it's clear that we have all the material needed, theoretical, to establish gravity, part of the Standard Model. In fact, the theory is already developed there, but nobody calls it or relates it to gravity. So regarding this anomalous gravitational constant findings, most of research relating or in connection with gravity, mainstream research, also using general relativity, tends to consider that there is such a thing as the gravitational constant. It turns out that, again, there are plethora of experiments and articles which document that the measured gravitational constant is by far not within the experimental errors. But these articles are again like implicitly ignored, and nobody really pauses for a moment and questions if the theory we are developing, it's really scientifically correct. I mean, since so many articles document that it's not a constant, then at some point we should stop claiming that that it is. Now, why it's not a constant? Because gravity is an average of polarization of nuclear spin corresponding to the divergence part of the hydrogen atom, unified field. At this point, I would like to mention that in the previous talk it was mentioned, well, gravity's permittivity coefficient. Indeed, that's what it is. First of all, the proton is not a separate entity from the electron. This is how we develop the theories. Theory of the electron on one side, theory of the proton on the other side. But no particle, whether electron or proton or neutron, first of all, comes just with an electric charge or with the magnetic moment. All particles come with both aspects, which show clearly that the field, whatever field that is, has a divergence part and a curl part. Of course, this is well known in mathematics. Any field can be decomposed in such two parts, with divergence and with curl only. That's called Helmholtz theorem. But it's not just the math. It's the physics nowadays that any particle will also, with or without electric charge. And by the way, no matter particle doesn't have electric charge. The neutron is not neutral. And now if you might think, well, what about photons? But those are bosons. Those are a totally different thing. So all matter particles, fermions, have electric and magnetic charge. Now, what's called magnetic charge is not what you expect in the Maxwell's equations. The electric field and magnetic field B are really curvatures, are forces. They are not really the sources underlying those forces. They are not the sources of those. So there is such a thing as a magnetic charge, and it's called and it's quantized, and it's called the fluxon, and it's at the level of the electromagnetic vector potential, really. Without going into details, coming back to this level, the hydrogen atom is a unity of quantum object, of unity of matter, and the electron is not a separated thing from the proton. So there is a much more at length explanation of this unification of electron and quarks, where the electron is really the fourth quark, and the usual quarks are really space-like quarks, three of them, which these explanations or this unification is explained in my articles available on Vixra and so on. Learning at the top level about these advancements, unifications, gives a much better perspective in which direction to develop the current theories. So, and it doesn't take much time. I mean, learning about this unification of electron and quarks could take 2-3 hours of reading. So back to the gravitational constant. Dozens of articles report the experimental determination of gravitational constant does not fit the standard value of and standard deviation corresponding to the measurement errors. So I said, community, those interested, readers, viewers, and so on, those, some of those, of course, are just enjoying learning from presentations, if you want. But on the other hand, writing a report, it's a lot of fun, and gives much more satisfaction. At this point, I would say, think of watching Zumba or work or Zumba dance and not trying it yourself. It's really the same thing. Or watching how others are training in the gym and just watching. So I'll state it as a homework. Write a report or article documenting these sources and articles. For example, even Skydermo's articles are not really enough, let's say, not polished, but structured to become some articles you might want to use as a reference to direct towards the original sources of experiments which document that gravitational constant is material dependent. So as a partial conclusion for now, gravity is an electric type of force due to the spin polarization of nucleons and averaging to a weak force from the strong nuclear force in the quark model of the standard model. I want to emphasize again that this is so clear that it's just a matter of bringing it to a larger public. At this point, there was an attempt, I mean, not attempt, a very solid development of the theory by Abdus Salam and collaborators. And I recall that Salam was one of a co-author of the electroweak theory. And in the, I recall, like 70s or 80s, he formulated a strong gravity theory, explaining gravity as a byproduct of nuclear force. So this was already done in the, I don't know, maybe 70s. But how is it possible for such a breakthrough to be completely ignored or forgotten? Well, that's a different story. So strong gravity is really the technical theory developed on top of the strong of the standard model, which I would probably have to look into more detail to see how it can be connected with the intuitive picture which everybody gets, that gravity is really a nuclear spin polarization effect. The problem with incorporating that direction of research is that it's probably formulated in terms of differential geometry, gauge theory language, which is, I would say, not outdated, but no longer necessary to formulate a theory of gravity as a polarization of nuclear spin. So let's retain this early theoretical development by Salam of strong gravity and go back to the Alzafon core finding, which is the experimental result. Dynamically polarizing the nuclear spin results in a change in the weight. Now, if you look at the whole story, with which is, as I said, explained by David Alzafon in the book, this is a very solid example of applying the scientific method. First, you start with the observation, which gives you some ideas of what's going on. Then you formulate a theory, and then you verify it experimentally. The observation part is kind of cheating a little bit, because Alzafon used some data available from Air Force chasing a UFO and so on. So again, I'll let you read the full story in the book by David. Also, mentioning this kind of observation, which is really cheating, looking at how others did control gravity, is very difficult to sell in scientific publications. So that somehow has to be omitted, and we have to do the work ourselves and develop the theory and redo the experiments. At this point, Mark Sokol and at Falcon Labs is working and doing, it's working a lot in trying to replicate Alzafon's experiments. So that's a good source of information regarding that level of development. But taking into account that this is already well taken care of, the origin of gravity, the experimental proof, I thought it's time to go beyond the experimental stage to what I call the technological phase of implementation. So I started to learn about advanced materials, solid-state physics, and so on, and presented some key points to be investigated by the engineers who design and manufacture new materials, and how this connects with controlling gravity. This is explained in a presentation, ROCAM, so Romania Conference on Advanced Materials 24. Then there are many more detailed explanations in the Tesla Extraordinary Conference 2025. So I encourage, if you're interested, there you have it. And back to this important point, how you may choose to help And this involves not just the readers and viewers, but also the researchers, to learn a little bit more what it's already known, and then continue this cycle of research and development, and then disseminating and teaching, and then helping others, which is what's called service to the profession. And as a professor, by now I realized how important it is to mix all these things: teaching, teaching, research, and service. And I usually think research, teaching, and service, but it depends on the on a case by case interest and so on. So let's take a look at research and development, the mainstream versus independent research. At this point, as a general culture, if we're doing science, I would say that the book by Thomas Kuhn, The Structure of Scientific Revolutions, is a must, but not to read, because it took me quite like a week or so to read it, browsing and so on, extracting the essentials. And if you're interested in just a brief synopsis, there is a recent presentation to a history of science meeting that I went and presented, where we see some key ideas, among which are the following. Science paradigms evolve similar to biological species and have a lot in common with politics. And I'll leave it at that. But with the what do we take from this? That we need to collaborate. We need to establish groups of researchers having common goals and supporting essentially the same theory, which starts to resemble to how political parties are. What's the function of a political party and so on. So too much fragmentation of research into independent researchers going in various directions will not have the same impact as in the case where we try to build teams working on a certain direction, certain theory. Well, at this point, I should, of course, recognize that we love to do research, and being so much fun, we kind of like to be left alone and do our developments, and it's natural and there's nothing wrong with that. But again, is it possible to engage a little bit of service to the profession? Well, we'll see. So, on the other hand, developing a theory which is almost completely detached from a mainstream scientific theory, like the Standard Model or general relativity, has a lot of drawbacks. And to advance science overall, one needs to do a research and development which is compliant with some mainstream science. So, bottom line, I feel like I'm preaching here, but from just research and development to go to learn, research, develop and disseminate, then teach and service. And of course, refining such denominations is something we see going on in various directions. So it's normal to see a more complex structure, and including in how our activity is structured. Then, of course, I have some suggestions for research and development that would help. And here is my apology. So studying such exciting topics and novel approaches is tempting. Yes, it is, because it is the journey, not just the destination. So we all understand that. Each of us with our own journey. But there is a need to collaborate and contribute to other researchers' work to achieve a consistent new theory rather than scattered, author-dependent formulation, etc., etc. And let's come back to some more technical material. Developing the theory of gravity in balance or in consistency with the standard model of elementary particle physics. That would upgrade and mark a new level of this standard model, which is stagnating significantly since the 1970s, after the Higgs boson was found and so on. And at the same time, if broadening the range of phenomena one considers, in order to compensate the separation of theories due to separation of experimental approaches, then one should learn a little bit more in neighboring sciences. For example, the physicists to learn more chemistry and biology. And I would say mathematics it comes later on, when you really need to implement it in a formal way. And although some mathematical frameworks can help from the beginning to know how to think about the corresponding unifications, it doesn't have to be, mathematics doesn't have to come first. It's not the equation that matters. And now I recall hearing Mikio Kaku saying, I want to know the equation which rules the universe. No, it's not the equation that matters, but rather top-down principles, and what's usually called the conceptual interface of a theory. And speaking of principles, Pythagoreans, got it more than 2,000 years ago. Number rules the universe. So Zeno, with the indivisibility of infinite indivisibility of action, of motion, already got the idea of quantum of action, and so on. Much more to be said, that the ancients had quite important ideas and, if you want, philosophical understanding of how the universe works. So it's not the equation. What is needed, and it's already done in considerable amounts, by my research in the articles I already made available, I'd say published, but not peer-reviewed, is a conceptual, reformulating the conceptual foundations of the standard model. And here I just included a few important ones. First of all, there is no such thing as space-time continuum. Not a continuum, and there is space and time are not really physical concepts, but rather emergent and mathematically formulated concepts. What establishes clearly in the science of the 21st century is the use of the network model. It's so everywhere that it's somehow amazing that we're not learning from this lesson to downplay the idea of space and time. Then upgrading the role of Feynman diagrams and the higher version of quark line diagrams. One should look at the developments in quantum computing and quantum computing hardware, where you see clearly that we are building some networks which process quantum information. And this, of course, reflects that in nature, because we are essentially copying and looking how nature does it, and then we try to replicate it in ourselves. So nature is just networks and communication, and nothing to do with space and time. Space comes from our habit of measuring distances between objects, geometry, ancient geometry, Euclidean, and so on. Of course, you want to know when you buy a couch, you measure the door. Will it fit through the door, and so on? So it's so practically oriented that it's ingrained very deeply in our minds, and we think that space is something real. No, it is not. Time also. Clocks are made exactly to create time. And Einstein said, well, the illusion of time. So he had also an understanding of this. But we don't have enough time here, nor the purpose of this talk is to mention this. But if you're interested, go to articles and read about how the space and time emerges from the quantum computing flow of Heraclitus, who said, Pantare, everything flows. There is only the change. So how does stability of objects and what we think reality is stable emerges from the flow? I preliminarily explained it in one of those articles. Another misconception, starting with the 1950s, is that quarks are particles. No, quarks are not particles, but rather principal directions of the field of an hydrogen atom. Think of pictorially that there are like 3 tornadoes emerging from, say, a proton or neutron. And the problem is the electron is a 4th quark, but at the present time it's not clear how to take those 3 tornadoes to close them and generate reasonable technical model of the hydrogen atom, which also upgrades the electronic orbitals models already in use. What is clear is the so-called Hopf vibration is essential for that. And again, I give some hints here and there in some articles. But bottom line, without the technicalities and the need for peer-reviewed new model of the hydrogen atom, we can retain the natural, almost obvious fact that quarks are not particles, are directions. And they have a spin of those tornadoes. Spin is everywhere in quantum physics. It's associated with helicity and all that. Then another important unification of atomic and nuclear is this important new breakthrough that the electron is really a fourth generator, which is time-like. What it really generates is the quantum phase, like a clock attached to the atom. A clock that it's almost obvious is what Einstein said about any coordinate system. You have to have a clock and you have to synchronize two such coordinate systems, reference frames, in order to make sense of the idea of time. So this quantum phase, it's really a proper relativistic quantum order parameter, which is also intuitively explained by Feynman in his QED book, saying that any particle carries like a tiny clock with which measures time, and it's related to the quantum phase by the formula exponential of EI omega t. So this was already understood in the 70s, the relation between quantum phase and time. But now it became quite clear, almost obvious, that there is no such thing as a linear time, and the only order parameter, it's a proper order parameter. Each particle has it, each matter particle has it, and it's abstractly called quantum phase. Then an intuitive image is that the universe looks three-dimensional because of those three quark directions. But then there is no fourth dimension as a time dimension, but rather that each matter particle has a vibration aspect, periodic change, which you could call it vibration, which justifies again an intuition of another famous researcher, Tesla, who said, if you want to understand the universe, look in terms of vibration and energy. These are lessons who should not be forgotten, and when developing a theory, one should look at what these giants said before us and not disregard that. So what about the technological advancements, or rather, what's the technological level for the research in gravity control. And here I'll just point to the highlights, point to the stages. First of them, again, 1970s with Alzafon. Let's say we need to perfect the methodology of nuclear spin polarization. That's also referred to as dynamical spin polarization in the theory of Alzafon and his experiments. It's quite widely used in nuclear magnetic resonance, measuring chemical shifts and analyzing materials. Also in magnetic resonance imaging. So we have not just the technology, but the whole infrastructure is so well developed, except nobody thought it might connect with gravity in some way. But then there is the other part. Higher temperature means separation, decoherence, gases, Brownian motion, and so on. So you want to avoid such phenomena because then you cannot align the spins, really. So then you need to include what aligns the spin. First of all is rotation, which anybody who played with a gyro clearly understands. If you want to maintain an axis, then you have to spin the object. Then the second is supraconductibility. So if you want to have a phenomenon without friction and decoherence, loss of properties, and so on, then one has to lower the temperature at the level of supraconductibility. Then look at the papers by Tashmar, work by Podkletnov, Ning Li, and so on. But then there is the next level, which is really new. There are lots of achievements in quantum computing hardware and two material science and design. Quantum computing reached the level of manipulating individual nuclear spin, which means we can orient the spins, nuclear spins, one by one. Now, that technology exists. So how can we use it in connection with gravity control? And then learn about these two-dimensional nanomaterials, which have amazing properties precisely because they're already polarized in 2 dimensions. So you have covalent bonds in 2 dimensions, and then the third one is automatically polarized perpendicularly to the corresponding surface. So I think I give you the synoptic view of what is the status of gravity control, gravity theory and control and technology. And it involves a lot of learning of what is already documented and published in articles, and then try to help developing this new this direction from the level it is already. So with this, I'll just leave this slide on, and feel free to share the PowerPoint presentation. I think it's about time to stop. Tim, What do you think about that?
Yeah, well, we are running a little bit behind. I didn't want to cut you off, but we do have Jenny. But yeah, I think
I really appreciate it. Yeah, and I saw the message. Okay,
no,
it's time to
you know
stop.
what? And I am so overjoyed to finally have you on APEC and presenting about this material. And again, one of the things that I want to do is create some breakouts for this, and I'll try and do that over the next week. I've got film footage I'm working through for other things as well. So there's a lot there. But the work that you're presenting on is like brand new to this community, unless people have been following you. And I know a lot of people do follow you from your past work, right? But for APEC, it's new. So thank you so much.
Sure. Thank you again
Yeah,
for this
let
opportunity.
me bring everybody in. I'll take out the slideshow. And guys, put your hands together and give Dr. Lucian
Thank you so
Ionescu
much.
an enormous applause. And again, a giant thank you, sir. It was absolutely wonderful having you on. I would love to drag you back into our program in the future. And so since we are a little bit over time, what I'm going to do right now is take everybody out, and except for Jenny. And Jenny Nielsen, thank you so much. And I am so sorry about the delay. We've just been pushing things a little bit behind. So, Jenny, I can't hear you. Your mic is not, Jenny, your mic it's on, but it is not connected. So if you go down, no, if you go down to the bottom bar, you should have a little mic with an arrow button, and that'll let you change your settings. Or if you click the gear button, try the gear button. You may have to select a different mic. If you click settings, it'll have the mic and the speakers. And it looks like you're okay. Nope. Okay. Jenny, can you hear me okay? There we go. Okay, you're back. Your mic is not. So again, can you try and click the gear button? Yeah, and no stress, no stress. Technical bugs are part of the APEC program and have been for 5 years.
Oh.
There we go.
Can you hear me now? Okay, yeah.
I can. Yes,
think that you should be able to hear me now.
Yeah. No, you sound
all right.
great.
Awesome. Fantastic. Okay. It's great to be
Perfect.
here.
Yeah, Jenny, thank you so much. And thank you
All
for
right.
the short notice also. We had Robert Francis Jr. was going to do a presentation on magnet drop
all right.
experiments.
And
He
remind
wasn't
me
able
how
to
great to
complete
see
it.
the previous speaker a little bit.
Okay.
Oh man. Well, maybe he can come back and give more.
Yeah. Let me take myself out, and your bandwidth is a little low, but you're doing okay. And so I'm going to take myself out and take it away, ma'am.
All right. Thank you so much, Tim. Okay, so I'm Jenny Nielsen. I'm a PhD candidate at the University of Kansas. I'm actually double ABD in physics and philosophy. I have a Master of Science in Physics. I have a Master of Arts in Philosophy. I have a Bachelor of Science in Physics and Math, summa cum laude from the University of Missouri, Kansas City. That's me. I have a topological unified field theory on field papers that you can read. And that's me. Happy Gratitude Day weekend, everybody at APEC. So I'm here today to talk about topological torsions and warp bubble physics. If everyone, you might have seen how if everyone's seen Hal Puthoff in Age of Disclosure, you might have seen him talking about warp bubble UAP physics. You might have seen Jack Sarfati talk about torsion in his recent talks, and you may have seen lots of different approaches to Alcubierre drives and such. What is a warp bubble? So basically the idea is that you warp space-time around an object, and then you can do things that you couldn't normally do, and then feasibly the people in the craft wouldn't be impacted in the same way as the space-time around it, so they could be zipping and zapping and doing all kinds of crazy stuff in our world, but where they are, everything's fine and they're not experiencing anything strange. So that's sort of the idea of how you could do a warp bubble and then control a ship with this warp bubble. You could go different places, discomfort. So that's the idea of a warp bubble. But actually, I'm going to start in 1964 with this weird experiment with a guy named James Edwin Barger. Long story short, a long time ago, back in like 2012, I was probably a little bit goofy, staying up really late working on some plasma physics, and somehow I found this weird paper by James Edwin Barger, and I got the heebie-jeebies because for some reason it resembled what I thought maybe a UAP system would look like, and I didn't really think that he was like doing UAP physics, but I just got the vibe that, holy crap, I'm looking at something very Philadelphia experimentish. And so I saved the paper, and then I lost the paper, and I just found it a few days ago again. So it's a cavitation paper. It's called Thresholds of Acoustic Cavitation by James E. Barger, April 1964. It's an Office of Naval Research privately distributed paper. I'm not sure if the paper was ever formally classified. I think I'm in a Faraday cage in this building. So I'm not sure if the paper was ever formally classified, but it was like a privately distributed paper. It's kind of hard to find except on .mil sites on the deep web, but not super classified or anything. You can find it. But anyway, it's a thresholds of cavitation experiment. What's cavitation? Cavitation is what happens when a liquid, water, is locally pulled apart by pressure waves. Whoa. By pressure waves so violently that it forms vapor pockets or voids. So basically, you have water, you put pressure on it, and it starts separating and forming bubble pockets inside the water. So think of rapid pressure drops that can cause cavitation. Liquid can't hold itself together. Microbubbles form and collapse. Enormous energy release. So it's like an ultra-fast shock structure, and you get wild symmetry patterns. It's similar to cymatic shapes that you're used to seeing in water, and Bessel functions are causing these cool, fancy shapes under cymatics, but cavitation is a slightly different mechanism, I guess, causing the thing. I mean, it is a different mechanism, but I'm trying to think of the right word. But anyway, in everyday life, cavitation occurs behind boat propellers, in ultrasonic cleaners, and collapsing bubble jets, in high-speed flows. And acoustic cavitation is like the most common kind. That just means cavitation caused by sound waves. So the Barger experiment, in 1964, Barger performed one of the earliest flash photography experiments that studied this. This is a modern piezoelectric image here from a recent test, but it's similar to what he was doing. So he had a point-like transducer emit a single high-pressure acoustic pulse into water. The medium had a compressive front followed by basically things just got condensed. The rarefication triggers the formation of a simple spherical bubble boundary evolves smoothly, and so usually you get one shock front, but they got weird stuff. So they got a central bright flash region, a set of nested discrete shells propagating outward, not 2 shells, not 5, but 20. And this wasn't expected, and they weren't evenly spaced either, and they fell into 3 cluster regimes of different shapes and types of shells with different spacing laws. And none of this looks like conventional physics. I think it's still cutting me off here with the Faraday. So why were 20 shells not expected? Let's see. Reason one, Rayleigh-Plesset, that's the standard way of modeling this kind of water behavior, a violent pressure spike outward, and that's it. So you don't get repeated discrete shocks. You don't get the quantized shells that almost look kind of quantum. You don't get modes locking together. You don't get interference structures. This quantum type behavior is really odd. And the funny thing is like you can apply quantum modes of water to try to understand this stuff and it still doesn't make sense. You can apply Bessel functions to understand this thing and it still doesn't make sense. You can apply nonlinear behavior, Navier-Stokes, acoustic standing waves, just you can do any kind of classical physics, any kind of quantum physics we got. It never makes sense. And so, yeah, this is just the same kind of thing. So Navier-Stokes doesn't produce it. Nothing does it. But there's a topological explanation now. If the internal state of the water includes a geometric or phase-like degree of freedom, the collapse event would release discrete eigenmodes. So you get d mu d v phi rt. That would produce spherical pulses with quantized radii, limited spectral range, about 20 modes in this shape, and a natural grouping into spacing regimes. So a quantized torsion or phase mode, it's actually omega, not phi, but whatever. A phase mode cascade provides a direct interpretation of Barger's observed shells. Or actually, maybe it is phi. I'm just like having a bad day on my Greek letters. So anyway, what Barger saw, this is what he got. But TOFT says you're going to get this thing to x to the mu equals exists on S1. So the field couples to torsion through the projected S1 fiber of the bundle. During cavitation collapse, the internal phase is not smooth. It gets gradients and defects. When the bubble collapses, these gradients discharge as quantized torsion eigenmodes. So eigenmodes is basically harmonic frequencies in my theory on Beltrami modes of the hot vibration. So if you put a flow over the hot vibration, the flow has harmonics, and the harmonics have eigenvalues, which produce eigenmodes. And anyway, this is the hidden variable not classical fluid mechanics does not have. So this is why, in my opinion, this is happening. This is the only explanation I've come up with, and I've looked at this thing on and off now and then for about 12 years. So the key prediction, only the first 20 modes fit a 1 to 3 centimeter water shell. And I know this is kind of boring, but we're going to get to the cool stuff in a few minutes. So in a spherical medium of radius r, the torsion phase modes obey this delta second order delta thing times this thing times the yield spherical eigenvalues. But TOFT modifies this with a torsion coupling cutoff. You take the absolute value of the delta thing minus delta tau, not minus, less than delta tau, and then you get that approximately to 1 over L. It's not L, whatever, torsion. And then using measured energy, no, it is L. Torsion densities in cavitation. Barger's geometry, the larger. I never memorized all the Greek letters. I do on and off, and then I forget them. Anyway, this cutoff arises because the S1 fiber curvature projects only a finite set of harmonics into 4D. I gotta remember to do that. So why the shells group into 3 regimes? So the 20 eigenmodes divide naturally into low-end regime, long wavelength torsion pulses, wide shell spacing, mid-end regime, resonant modes, nearly even spacing, and then high-end regime, like this, close to curvature cutoff, compressed. So this is exactly the distribution that Barger got. And I think that since it matches identically, that this is another cool experimental quasi retrodiction of TOFT. So it's like, I didn't ever think that TOFT would actually solve this. I wasn't thinking about this when I developed TOFT, but hey, TOFT explains them to me. Anyway, and TOFT So the clustering corresponds to the three different coupling strengths in the dispersion law, where alpha and beta keeps the first term, no clustering. So basically, like it's an expanded version of the classical acoustic dispersion law, and really pretty that we get this, and kind of special. So Rayleigh-Plesset gives single shock and ripples, but TOFT gives us the cavitation that we actually see. And since this is an unsolved mystery that we just solved, this is another verification that TOFT probably is the right theory, but you know, we need more. We need more data, we need more verification, we need more peer review, we need more validation, more people replicating this stuff. But this is a good sign. Anyway, but let's go sci-fi. So in TOFT space-time manifold, the total manifold is S9. You know, me and Martin Cupa, we argue back and forth like whether this means that there are extra dimensions or whatever, and he would rather do everything on a little Clifford torus or whatever, so that you only stay within 40. I say, screw that. I like higher D. But higher D, I'm holding my cell phone up to try to escape the Faraday cage. But higher D doesn't mean necessarily like we're literally like, I mean, I think we are flatlanders, but you don't have to think of it like that. You can just think of it as extra mathematical tracking indexes. You can think about it like that if you are uncomfortable with the idea that we're just flatlanders in a higher D world. But I'm pretty sure we are flatlanders in a higher D world. It makes sense to me. Why wouldn't we be? Like, why wouldn't there be extra levels of this world that we don't perceive? So the space-time manifold with base CP4, that's just the four-dimensional, really eight-dimensional complex projective space. It's four-dimensional in the sense that it has four complex dimensions, but those hold 2 dimensions each because they have a real and a complex number in each. And then fibers S1, phase e to the I generating U1 EM and temporal twists. So yeah, that's my theory that we've talked about before. Then so world lines or fermionic paths, well, it's really any particle path as embedded in R to the S9, knotted link to form vortex atoms. It's really embedded in C, but whatever. Anyway, torsion, you get this torsion lovely equation. I'm not going to bother saying that out loud, but in TOFT, the fiber-induced contortion K equals 2 times the regular T, where T is the Nia-Yan 4 form, T equals this beautiful thing, modulo exact forms, linking EM torsion to the gravitational twist. So basically, if you do enough with EM, you can kick up gravitational torsion. Because in my theory, gravity has torsion because basically every field has a twist, and the twist generates torsion. And you have to have twist because there are all kinds of effects like Aharonov-Bohm and charge quantization and all kinds of things that only really will turn up in your theory if you add twist to the single field. Otherwise, you have to chop it up into little micro fields and patch on algebras and do all kinds of things that break up the unity. And why would you do that? You want one field anymore if you do that. Anyway, okay, I'm gonna practice my yoga here. So the cavitation experiment analogy, you get sonoluminescence or vortex. So basically, okay, what is this? Let's see if I open the door, if I get. Okay, so anyway, here we go. So assume a spherical, whoa. Hold on, I'm waiting for this thing to load. Why isn't it going back? So
Well, Jenny, hold
So
on just a sec. If it's
essentially,
okay,
if you
hold on.
pump
Let me stop your camera, okay? Or actually, can you stop your
a
camera? And that'll free up some bandwidth. It's not preferable, but
UAP. Well, take a UAP and
okay. Sorry, you're still having issues. Jenny, can try stopping your camera. Leave your mic on, but stop the camera, and that should free up some bandwidth for you. Jenny, you've muted yourself. Jenny, you've muted yourself. Okay, Jenny, there we go. Try stopping your camera. Try stopping your camera. Turn your camera off.
Oh, can you hear me now?
Yes, turn your camera off.
I can try to turn the camera. It just says stop. Okay.
Yeah.
Okay. And then
there
I
we
can
go.
try
There
to.
we
Should
go.
I try to proceed with no camera?
Yeah. Go.
Yeah.
No,
Okay.
you're
Perfect.
good. You're good. You're good.
Have you guys been able to hear anything I've been saying?
You've been cutting
Have you
in
guys
and
been able to
out.
hear?
You've been cutting in and out, but this should help.
Okay.
This should help. Okay.
Okay. Fantastic. Okay. So basically what I've been working on is taking this Barger thing and thinking about what's happening there. And if torsion is coupling to the sound waves and couple in water, this implies that there's something happening in water that couples to torsion, which means presumably there might be a way to kick up torsion using water. And if we use EM, presumably we could kick it up even more. And so that's kind of where I'm thinking about this. And so I'm kind of taking on a sci-fi application. I'm not necessarily saying aliens are really doing this, but maybe aliens are really doing this. I'm not saying it's aliens, but it's aliens. Anyway, so EM torsion coupling. So it's stronger than acoustic, which is just a little bit perturbative because EM directly modulates the S1 fiber phase theta, and that induces global topological defects. That means like Aharonov-Bohm like phases in the bundle, but also other things because TOFT isn't limited to just that. So the cavitation experiment analogy, somoluminescence or vortex excitation in fluids, or cavitation in fluids, excuse me, translates to creating topological voids, regions of zero linking, and the world line bundle based, but it's literal space-time cavitation, pumping torsion to unlink local world lines, forming a spherical outer defect that warps the 4D projection around your UFO, or UAP, since we're cool now when we call them UAPs. So this is how we would create a bubble warp drive, like what Hal thinks the UFOs are using, sort of like what Jack thinks the UFOs are using, although Jack is probably using a slightly different mathematical formula than I am to generate this thing. So assume a spherical UAP core, radius R1. I need to catch up with Jack on how he's doing it right now. So radius R equals 1m, modeled as S3 in the S9 embedding. So I have a 9D world. The 9D world, we're embedded in the 9D world. I'm agnostic as to whether we're flatlanders, although I kind of personally believe we are. But like as a scientist, I just believe it's like you can use these things as indexes to track are real, but as a person, with a water shell thickness of, delta equals 0.1 meters for dielectric containment and cavitation mediation, not millimeters, meters. So the water acts as a classical proxy for bundle density, high permittivity, and that will enhance the EM fiber coupling. Fiber just meaning like a chunk of space-time. Essentially, the space-time comes in these fiber-like chunks, in my theory. So the classical proxy for bundle density use EM induction, not acoustics, to couple the torsion via the fiber's Chern-Simons 3 form. That's just the twist, where A is the connection lifted to the S9 bundle. So those are just ways of talking about topology. But basically, you're kicking up E&M to vibrate the cavity that's filled with water, the shell, and then you create cavitation in there, but also what's happening is you're coupling to torsion. And this is just kind of weird. And like, when I was thinking about this, I was like, why would we do it this way? But we're going to get into that a little bit later. Anyway, embed the sphere as a hot fiber, but S2 is the real way of looking at it, the real number way, representing a stable soliton, linking number LK equals 1, mass M, basically just these are ways of thinking about these things mathematically, but essentially you're just thinking about the sphere, you're vibrating it, you inject seed torsion via a central coil, you apply a rotating EM field B equals this thing, and then you couple to the fiber phase as that thing, and then you complexify it for the Hopf twist. You're just looking at the wave. It's complexified because waves are complexified. You don't have to think of more the Hopf twist. It's just that it is a Hopf twist because that's how fields all look like Hopf twists. If you really think about it, like we think of these fields like the heart field. Everyone calls it a toroid, but it's really not. And the Hopf vibration is this thing that I don't know if I even have a picture of the Hopf in here. I hope I do. Math torsion density is this thing. Then that creates an unlinking, and then you get a cavity. So basically, you're creating a change in space-time structure. So you surround your core. This is just kind of that. So that was the math. But what you've done is you've surrounded the core of your UFO with deionized water shell to minimize conductivity loss. Water's molecular dipoles align with the EM fringes, proxying a dielectric bundle sheath that stabilizes the defect. So you induce shell cavitation using radial EM waveguides, toroidal antennas, they're really Hopf antennas, at a shell boundary to generate standing waves. The 2FT coupling, EM field lifts to bundle connection. Really just what this is really saying is that the M field is working on the bundle, and the connection is just a way of looking at the twist and the way that thing turns, where shell permittivity amplifies torsion flux. This shell's the core. It's just spherical topology. What basically it's saying, it's separating what's going on in the core of the UAP to what's going on in this shell. And the shell is going to interact with space-time in a unique way. So you EM pump to torsion, which is stronger than acoustic. This is all fancy language, but essentially what ends up happening is you get warp activation and propulsion. So when the torsion is over the 2 pi, the core shell boundary forms a topological, a linking defect where world line shortcut via the fiber projection, contracting effective 4D distances, getting an Alcubierre-like bubble without negative energy, and you get this warp factor. The really interesting thing, and I didn't run it, is that you don't really need a lot of EM to do this. You don't really need as much as you might think. And I need to run that, how much EM you need. But anyway, induced line element, you get this, where contortion is this. Schenk's radial GOD6, you get contraction, asymmetric torsion pump, yielding thrust. From linking momentum, you get the idea, boom, because it has a warp bubble now. Anyway, these are the core equations of how to get your effective metric, your thrust, your torsion form, your fiber phase, and yada, yada. What's interesting is we have noticed that these weird UAP things turn up off the Southern California coast in water and in other areas with water. My brother and mother and dad used to watch this eagle cam on Catalina Bay, and one day they saw one of these weird metallic balls come out of the water behind the eagle cam, and they all shrieked, and I heard them from the other room, and they're like, Jenny, come, and I come, and of course it's gone. They're like, of course it's gone when Jenny comes, because I'm the scientist and I could have explained it. But it's like the singing frog, they have the paranormal experiences, and I'm not there. But anyway, my brother's like, you would have finally believed me that but Gas, or whatever his sister's name is. But so where did they, yeah, so but yeah, I'm kind of open-minded, especially now after I've learned a lot more physics. So if the aliens are visiting Earth, what would they do to refuel? If they don't need plasma, maybe they would just go and dive under the water. And like we talk about, like there could be alien civilizations under the water. I think it's more likely that they would be visitors from other worlds and they would just need water. But you know, whatever. It's possible they could live underwater too, but I just like, it would be very weird if we were sharing the world with other creatures. Anyway, why water is the perfect alien medium for creatures who want to visit. It's a high dipole moment, strong EM coupling thing. In TUFT, the U1 gauge fiber phase this way. Dipolar molecules amplified in bubbles. Most fluids cannot form perfectly symmetric collapses, the cavitations. Water can. No need for high temperatures or plasma. Plasmas are chaotic. Cavitation wants coherence. So water gives stable density, predictable response, smooth radial collapse. Water is essentially a room temperature space-time lens. That's weird, but it kind of works that way. And also, water's cool, right? Life came from water. Let the waters bring forth life, evolution, all that jazz. So water might be cooler than we thought. What the Barger experiment really demonstrates, Barger's 20 shells show that a spherical collapse does not produce a single shock, but a discrete spectral cascade. This is how you explain it. The collapse mode dumps. You get inner shells, middle shells, outer shells. It's a topological event. Aliens don't care about the fluid specifically. They want a torsion cascade. Where did it go? Let me see what happened here. I'm freezing. The goal is to exceed the threshold because that topologically re-identifies the S1 fiber over the 2 sphere. That's actually also condition. So you're not only getting a warp bubble, you can also go a bit further and get a wormhole. It's kind of almost equivalent in TFT. So you get a Barger style cavitation, U1 pumping, and let's talk about how these paces fit. A EM U1 pumping provides phase bias in the fiber. The fiber phase directly does DO equals A plus F, not DO, D, theta. Apply a time-varying EM field around the spherical craft, radial ERT, tangential B, theta T, does 2 things. So it pre-twists the S1 fiber. The field creates a global phase gradient around the sphere. Delta theta is not 0. This is like winding up the fiber, and it sets the sign of the torsion. So you can control what the torsion is doing. The EM field, hold on. More detail than this. But I just really started exploring this. I can't see my slides. 1 second. I will be able to again soon. I know what's going on. They're too small. I'm making them bigger. Whoa. Okay, I went back too far. So we set the sign of the torsion. The EM field biases the collapse, so all torsion modes add constructively. Without EM pumping, the 20 Barger modes partially cancel, but with EM pumping, they coherently add. So we get more torsion and more torsion and more torsion until we have done something to the space-time field that is really cool. The cavitation collapse supplies a torsion spike. Now the aliens trigger a torsion collapse. They generate a perfect spherical acoustic impulse from inside the water shell, a bubble nucleus, it expands and collapses violently. Water being polar magnifies this because EM field modifies dipole alignment. Dipole alignment changes the phase stiffness. Phase stiffness intensifies torsion curvature. This is analogous to tightening a drum head before striking it. So the combined effect, a topological torsion burst. When the cavitation collapse happens inside an EM prepared water shell, it produces coherent torsion modes, constructive phase summation, spherically symmetric torsion wavefronts. The summed amplitude is this thing. And I keep seeing this thing that says slide 19, so I can't read my own slide. Come on, gang, let me read it. Not you. This slide. Thingamabob. So you get this constructive interference. You flip the S1 fiber unification on the sphere, you get a wormhole throat. Does it have to be water? Nah. But water is the best option because water is high dielectric constant, stronger EM phase coupling, water is strong cohesion, clean cavitation collapse. Water is stable at normal torsion, no plasma chaos. Water is self-healing. Bubble collapse geometry stays perfect. You could use ammonia, ionic fluids, plasma, but water gives the best topological coherence. Plasma kind of messes up the coherence a little. You could maintain it. Is this it? No. And I can't read the slide here because of how my screen to chat. I've also been doing some collaborations. Mark Sokol has bought a snow globe to start thinking about what's going on in the cavitation experiments. I don't know if a slow globe will work, but it's a fun place to start. And you can kind of see what's going on with the glitter when you vibrate it. So if spherical water shell plus EMU uncoupling plus cavitation collapse equals artificially induced topological torsion burst, artificially induced, whatever, it's natural. The torsion burst exceeds the geometric threshold, flips the S1 fiber identifications, yields a temporary wormhole throat. This is low energy, high precision engineering. I need to go through the joules. I'm sorry I didn't do that today. Not brute force. Aliens would pick this method because it's stable. It's cheap. It requires no exotic matter. Your exotic matter is literally... Let's do it. Maybe. Any questions? This is my topic, and I apologize that I don't have the actual joules worked out today.
So Jenny, you're all set. Was that that's everything? You jumped right into any questions, so I wanted to make sure.
I've also been doing line elements. Dan.
Can you hear me? Jenny? Okay.
Yeah, I can. You're cutting in and out a little bit. Yeah,
yeah. Your connection, it's better.
Yeah,
it is better, but you're still cutting out a little bit. Yeah, that is so awesome. Thank you so much. So what I want to do is, and again, I'm trying to kind of work around your connection because I think it's going to fade out again. So in this case, actually, it's 2:55. So I'm going to bring everybody in.
I can come back and do a more detailed.
Yeah, if you'd like to, I would love to have you back. And we'll maybe we can test next time. We could test a different location, see if your bandwidth works better. So, okay, well, let's do this. Before anything else, guys, let's all put our hands together and give a giant applause to Jenny Lorraine Nielsen. And so just to mention it, I am on a lot of email lists, and Jenny has been getting a lot of attention for her work lately, positive attention, great feedback. And so I'm really, really pleased, Jenny, that you were able to present today. Again, my apologies for the tech issues. It's been managed chaos as always, but
it's my fault. Yeah.
I would love to have you back though. Yeah,
I should have stayed at home and trying to go.
It happens. It happens. And I think it's aggravated by technology changing so rapidly that what works for everybody on day one doesn't work on day two. So, Okay, well, I think in terms of presentations, I think that was pretty much it. So,
I have something for Jenny, actually. This is an experiment based on her talk that we were.
Does anybody have any quick questions?
Jenny, I actually have the snow globe set up over here.
All right, yay!
okay,
That's
okay,
awesome.
good. Mark, here, I'll spotlight you.
I'm echoing. Sorry. Hold on.
Oops, that's not the spotlight button.
Yeah,
There we
so Jenny and I had a call earlier this week, and we were talking about different ways of basically finding the eigenmodes within a sphere of water and use the cavitation to create some sort of warm field effect. I don't know, if the cavitation collapses, you would see something happen. So essentially what she was describing was a snow globe. And she wanted it made out of crystal and quartz or whatever, but I just found a snow globe available on Amazon, and I stuck it on top of a large microphone over here that we had, or speaker actually, that we had from another sound experiment where we actually got objects to move. And I was just setting this up as she was talking. So far, I haven't been able to find the resonant frequency, so we'll have to come back to this a little later. I think it's probably way up there, but it's really, really loud. I was actually wearing hearing protection before like this in order to protect myself as we were trying to find that correct resonant frequency. Basically, what you do is you want the frequency of sound in water, where you'd create standing modes inside the shell. So it would be the wavelength of this snow globe, which is around 95 millimeters in diameter internally. I'm assuming based off of my guesstimation of thickness of the glass. Outside it's 98, so maybe it's 94 or something like that. That would put the resonant frequency way up at like 16 kilohertz or something like that, according to GPT, which sounds about right. The problem is the audio amplifier I have over here doesn't really put out that much power at that level. At least I can barely even hear that level. My audio ability goes up to like 16.3. So yeah, we're gonna play around with this, and hopefully the goal would be to get standing nodes of the snow or the glitter that's in there, and see if by just using sound frequencies, which are just pressure waves, we'd be able to move objects around, and that would be a proof of concept that we could probably use with electromagnetic systems in the future. But yeah, it's a great start for this experiment.
Actually, Mark, that's really brilliant. That's a really brilliant idea. I was just thinking about that. I'm like, what would happen if you put different? So you get your standing waves, right?
Yeah.
Okay, there's Jenny. Okay.
Jenny?
Yeah, it's really funny. I was talking to Mark, and he like ordered this thing within like 30 seconds of me describing it. Suddenly, it's like, look at the snow globe. I'm gonna get the snow globe. I was like, oh yes, this is great. Enthusiasm. I like it.
Yeah.
Yeah.
What's the point of procrastinating? There was only one available.
No, I think that would be really interesting. It would be really interesting to see. Yeah, I was just thinking about, like, we've had so many presenters talk about scalar waves, and this lets you do a 3D scalar wave.
I should have been talking on my phone and broadcasting the presentation on my computer. That's what I'll do in this situation next time.
Oh, splitting the bandwidth. Splitting them. Yeah. I get it.
That would have worked better. I can't load the presentation on my phone. It just doesn't give me that option. I don't know why. Maybe there's a way, but I couldn't convince it to. But yeah.
It's okay. Yeah. Again, Jenny, thank you so much for being here.
Dan or anybody else? Did you have any questions? Did anybody else have any questions?
Yeah, if you could send me that line element for that Alcubierre-like solution that you came to.
Oh yeah, for sure. I'll say. Well, I'll send you the slides, the whole slide deck. I think I sent you the slide deck already. I think you're on my email list that I sent the slide deck to already. Anything else?
I think I am all set. If you guys don't have any questions, let let me see. And so actually, someone in chat was asking. Let me see. Oh, John Brandenburg said hydrazine or 100% hydrogen peroxide. Scrolling up a little bit. Plasmas have to be kept at high pressure to get the same effects.
Yeah, that's true. That's true.
Yeah, and then someone's asking how the internal pressure of the snow globe will impact the pressure waves, or will it?
Yeah. Also, I'm wondering if the glitter will change things too. The glitter might impact the way cavitation happens, which is frustrating. But there are all kinds of things to consider.
Okay,
Also,
but
how leaky your medium is. Like not the medium, the glass. Like how leaky your glass is. The reason I like quartz is it doesn't leak. But then on the other hand, quartz is more expensive.
wait, but I just realized that this would put us on track for a cheesy holiday theme coming up for December.
Yeah, it goes great for Christmas. Like, look at that.
Yeah,
That's very Christmas, isn't it?
Christmas theme, sort of science.
Yes, it is. It totally is. Snow globe science. Oh my god. Okay, Mark, we got to get on this. We can do this.
Okay. Well, we're in lab update time, so this may qualify as a lab update.
Yay! All right. Yeah. So when is the next lab talk? When we talk shop?
Well, the open mic, the next open mic. Yeah. So before we go further, let me officially say we're in lab updates, so we don't have to act proper now. We just can't swear too much to get kicked off YouTube.
Okay.
So let me see. The next open mic is next week because I bumped it forward to travel.
Okay, that makes sense.
And I have amazing footage for Mark. Mark did one hell of a walkthrough on the DNP, and he did some test stuff too. He's got a really big, cool laser that he's doing triplet state electron stuff with, and so I was able to get good footage. The walkthrough makes sense. The other part, I'm going to have to trim it a little bit because it was a long test and there were periods where not that much made sense. But
Mark, lasers might be helpful too. Like I've talked about EM, but lasers are EM, so lasers might be better for like pumping the thing with lasers. Yeah, we want a laser. Sorry.
Lasers.
Is it a quartz ball or no?
You're asking like for
the snow globe.
Yeah, laser doing something vibrating.
It's probably low end ultrasound.
Yeah.
No, Dan's asking if it's quartz though.
I have no idea.
We don't know. We don't know what it is. It's just glass.
Cool snow globe.
It's a cool snow globe.
That's what it's called.
What a quartz or what a quartz one would do, given that it's a piezoelectric, and if that would change anything. Probably not, but
it says this gold is made of glass.
Piezoelectric is better.
It says that it's made in glass and it was designed in Vermont and handmade in China.
Okay.
Box.
Well, there you go. Yeah, I'm not sure what it would change for this. Quartz might be a little stiffer than glass, but then for what you're doing, it probably wouldn't matter. Then another thing, this goes back to some of my stuff years ago. Quartz will pass ultraviolet and glass will not. And so when I was doing UV testing on lifters, you had actually I don't know if I should say this out loud, but one of the best, I believe it's sodium vapor lamp, I think, don't quote me on that. It is a massive UV source, but it comes with the bulb has two casings. The outer casing is glass and it blocks the UV intentionally. They don't want to hurt people's eyes. They use them as outdoor lights, the old school outdoor lights. And so you take those, you wrap them in a handkerchief, crack the outer case, and the quartz on the inside passes UV, and you can ionize air like crazy. It'll ionize everything around it.
That's cool.
Yeah, I have one of those. I have a 1,000-watt rig, and I use Teflon as a reflector. That was based off of Tim's suggestion.
Yeah, they're dirt cheap. I mean, they've been making them for 100 years. They're dirt
Guys,
cheap.
guys, we're gonna have a UAP one of these days. You know we're gonna do it.
You mean
One of
we're
these
going to build one, or we're going to be visited by one?
maybe both and or either, but I think we'll have the warp bubble one of these days with one of these methods. I think we will. Maybe sooner rather than later.
Well, I'm not sure if you're familiar too much with the team like the actual how the momentum flow of a warp bubble is, but it's actually really close to some of some of the toroidal activity going on with a hot vibration that not a lot of people realize or even have thought about. And so you're one of the first people that kind of even get, so that should be explored more, especially in terms of like, actually that's something I'm looking in Pice. He talks about counteraction. I'm digressing. I'm kind of linking a couple.
No, you're not digressing, Dan. That's interesting. Gravity is a twist. Yes, I agree. Hit it right frequency to go. That's true. It will burst, and we don't want it to burst.
Wait, that's Mark clicking the button. Love it. Love Mark's too. Mark.
We will do good things. More good things are going to happen soon. Yes. Holiday magic will help. How the Grinch stole top vibration.
That's your fallback plan. Like that's how I'm getting to Mars. Holiday magic. Wait until Christmas to build it.
Yes. Epic. Okay, guys. I guess is everybody done asking questions? Dan, we need to reconvene on this what you've noticed about UAPs and pop. I'm really curious as to what you've noticed, and I bet you have intuitive.
And Jenny,
I don't want to take too much of these guys' time because we'll talk in the future.
Yeah.
The community building that's happening, and that's not me, and that's not even really APEC. It's just folks working online, collaborating, getting to know each other.
Tim, you did do this. No, you did this.
No, it's not. It's organically evolving. The community building is amazing.
Yeah, it is great. It is great.
Jenny, John Brandenburg has a question. Is gravity a twist?
Yes, gravity is twisted torsion on the S1 fiber, which is also where EM lives. So yeah, it's kind of cool. Gravity is actually also, you can also see part of gravity as an 8-knot on the same thing, but that's like the resonant mode on the thing. And then and EM is God, what is the kind of loop? The electron is a much simpler loop on the same thing.
I do like the connection to torsion. That seems like that was the direction Einstein was going, and
and Cartan and
Cartan,
and Jack. We all love Jack, and I think that the groups that have been looking at this behind closed doors have been stagnating for a while too, because we didn't understand torsion. So I think this hop thing will help.
Yeah, no, I think it's wonderful.
The open community is such a better way to do things than hiding and like looking at little parts behind closed doors and then having one person look at the part and like, what is going on? Like that's just not how science works. So this open communication is just better.
Torsion definitely does help with even just canonical warp drive. I mean, like there was a paper in that, and I think like 2008. I'd have to pull it up to tell you the author, and I can give you guys the DOI from there. But it was exactly about they basically just plug the Alcubierre drive into Einstein-Cartan equations, and just by having the torsion there, changed some of the dynamics a little bit and made it more tenable. And the worst possible case scenario being Alcubierre. So, I mean, I think once we start applying, into some of these more complex ones like Taylor and stuff, I think you'll end up getting like something that's pretty usable with tech that's more near term than people realize.
That's exciting. Yeah, I think that it's actually a lot easier to kick up torsion than, I mean, it's small. It's a small effect, but you can kick it up. And that's the truth about a lot of quantum-ish effects is that like they start small, but if you find the right parametric oscillator, you can increase the effect by just interacting with it constructively. And so Jack and I recently did a paper. We're still working on it. It's a draft, although we're getting closer, about how there are quantum effects in the brain just because you have all these little chemicals that are interacting in ways that create little micro coherent effects, almost certainly. And then, but because you have all these nonlinear oscillators in the brain, some of these are going to find resonant modes with the effects, just by random chance. And then those are going to pair off, and certain quantum modes are going to get amplified and kicked up just by random. And then you're going to have quantum effects. And so that's pretty cool. And some of this stuff in the deep UAP X-Files literature implies that maybe the aliens are communicating with like a sentient material in the UAP craft, and that interacts with space-time, and their brain is coherent, and the material communicates with the brain, and like it gets pretty wild. But maybe some of it's plausible, and maybe the aliens are doing something like wearing a headband, and it's like more like a neural link that's not necessarily like a chip. It might be like something that's reading your brain waves and then kicking them up and talking to a material which interacts with the space-time field, you know. And that's all very kind of sci-fi, but you know, you can get there.
Yeah,
It's
yeah.
not that, yeah, it's not
And,
that wide.
and speaking of Jack's work, I just saw talk about synchronicities. I
Yeah.
did an interview. This is a little bit off topic, but it kind of ties back into the Froelich condensates, maybe.
Oh, yeah, we were
I
talking about that.
Yeah, so the question was in terms of seeing the future and clairvoyance, or not clairvoyance, but communicating with others. My question was, okay, that seems like a quantum explanation, but how are you entangled with those other organisms? And
Oh,
and
yeah.
I had talked to Adam Curry. I did an interview with him. He's not a PhD, but he is very well versed in that area.
Huh.
And he had said relevance is more important than time or distance for psychic events. He said its relevance is, I mean, based on very large, rigorous studies. I asked him, I said, based on these studies in humans and in animals and plants, I said, what is the most important factor? And he said, it's not time, it's not distance, it's relevance. And that got me thinking. I was like, okay, relevance. I was like, so we don't have a good mechanism for entanglement, and we do have this. I was like, what if that's self-entanglement with the future? And that would go to the Froelich condensate, or as you mentioned, parallel resonators in the brain, right? Because they can be entangled with themselves in the future.
Right. Yeah, you could have self-entanglement. Yeah, entanglement isn't in time as well. And you don't even need entanglement. Like you not the non-local coherent field exists across all time and all space just on its own. You don't even have to think about it being entangled with anything. Like, I guess self-entangled is another way of looking at it. But like it's just this thing that's there, and it's already connected to every point in time, every point in space. So you're just, and the relevance makes sense because it's just a way of thinking about a correlation. You can think of relevance as a way of thinking about correlation. So yeah. And another thing about the psychic thing, and I know that like when you talk about psychic stuff, you get banned from conferences and things, at least if you're Brian Josephson, but like telepathy isn't as weird as you might think. You can code things with entanglement, but you can share states. So you wouldn't necessarily be in a code with someone or exchanging words, but you might be experiencing the same thing at the same time. And then part of your brain might be able to classically translate that into a code in your own head, even though you're not exchanging the code with the other person. So you might get a different word for the same experience, but you might be sharing the same experience, because the experience is more likely a state, like a field state, rather than a code, if that makes sense.
Yeah, that makes sense. That makes sense. So that what you're saying there, that could be super low bandwidth. It shares just enough so that you can experience the same thing, and then you create the words for it. So well,
exactly.
Jenny,
So it's not a word thing, which is what you hear
Drew,
with.
Let me ask Drew really quick. Drew, do you have a lab update that you want to do? Okay. Jenny, is it okay? Let's segue over to Drew before he strangles me.
Yeah.
Evening. Just setting up some graphics. It's been a really busy couple of weeks down here.
Yeah.
Can you hear me?
Yeah. And you're doing okay though, right? Like busy, but good busy.
Yeah, just super busy. Working on manufacturing and just all kinds of around the edges, and I pretty much nailed down the design. Got it for the 1 Newton thruster. So now I'm just kind of kicking around different things and different ways to demonstrate it. We've gone to, well, I'll show you in the update. As soon as I save this drawing, close that. And can I don't know, can I...
Oh, yeah. Yeah, go for it. Share your screen.
Yeah.
And we will come back to Jenny's stuff. Jenny, let me apologize for cutting you off. I didn't mean to. I realized that we were
at all. I'm just
getting ahead
interested
of
too.
ourselves.
Yeah, let me do that. Maybe this button. They don't say what they are.
Yeah, so again, it's if you click the plus button and then you do share screen. I think that's what you normally do. There, let me see.
Working on it. Almost there. Technology hates me.
There we go. There we go, sir.
Yes. Okay.
Wonderful.
Okay, well, we'll start with... No. We'll start with this one. Okay, I don't have a picture of the test rig, but this is the horizontal pendulum test rig, and there's a series of test articles in there. This is like 179, and then I burned up 179, so I had to switch over to 180, but they're identical. So what this is it's basically showing that when you turn on the power, it starts generating thrust, because this one's designed to pull in a direction so that real thrust is shown downward. And then when you turn off the power, which is here, this is a power off because it's just 0 voltage. It just kind of hovers and hangs out and goes back to whatever the free drift, the thermal free drift of the system is. Then you turn back on the power and it makes more thrust. Then you turn off the power and it just kind of goes back into drifty mode. Basically, it's making... I switched over to doing micronewtons per 1,000 seconds because it's a better overall way to compare stuff. But the short and long of it is it's doing around 500 micronewtons per 1,000 seconds. It will do this pretty much forever up to, I don't know, 50 or 60 millinewtons worth of loading. But the only important really thing out of this is it's in vacuum. In this green line up here, you see the green line, it's over here, green, pressure, torque. So it's somewhere around 8 times 10 to the minus 6 torr. So keep that in mind that you're seeing thrust on a very calibrated, very sophisticated horizontal pendulum. And then here's the same basic plate, only now we're at atmospheric pressure. So basically I vented the chamber and gave it 24 hours to stabilize, and it all comes to, happiness. And then basically turn on the power. And the tricky part about this is you have to turn on a whole lot less power because you're out in open air and things short out. It's a whole bad day. But anyhow, you turn on the power, makes thrust, turn off the power, stops making thrust. So now we have the same plate in high vacuum doing magical things, in atmospheric pressure doing lesser magical things. It's about half as much because the field is about half as strong. Because if you turn it up any higher, it burns it up, and then you're sad. And then the really cool thing is this is the same plate taken out of the chamber. We put on a US solid digital scale, and because there was, some issues with the wife opening the door and screwing up the test, had to do it in 2 pieces. But basically, the same plate over the course of 6 hours put on negative 100 and, what are that, 60, 70, 89, 189 milligrams of negative thrust. So it literally pulled upwards 189 milligrams worth of magic. And so I think it was Feynman that said, if you can't prove something 5 ways, it ain't real, or something like that. Well, here are 3 distinct tests, very different, completely different scenarios that show the same basic phenomenon happening. So it's got 2 more to go, which I already have done those. So I thought that was pretty cool. That's the state of where we are. So now I can do demonstrations of our impulse drive out in the open air. And I have since replaced the cardboard tubes with something a little less cardboard tube looking, but it's working fine. So that's what's going on down here in sunny Florida. Questions?
Well, thank you, Drew. Thank you, man. And I'm hoping we're working on it in chat. I'm hoping to plan a trip down there to get more super high def photos and video of your stuff as well. So if you're open to it, and you have sourdough bread, and we may be able to get Mark to come down now. You could have a sourdough bake off. Sourdough bake off. So, hey Joel, welcome, man.
Drew doesn't stand a chance in a bake off.
Yeah, and I have Lucy in here also if he wants to hop back in.
Keep talking, New Jersey. Keep talking.
He has his. Oh, I can put it.
Sure.
Yeah, well, it's up to you, sir. You don't have to be here, but if you want to, yeah, it's just lab updates. I think, Mark, do you have a lab update other than scalar snow globe?
Jenny, approve that name, the scalar snow globe.
Scalar snow globe.
I approve the scalar snow globe.
Well, and Mark also has the Jewish space laser.
Mark, you ought to turn that thing over so that the glass is in contact with the speaker.
Yeah, but then you can't see it.
Okay, I'm going to tell you that, buddy.
It also kind of blocks all the air from going through the speaker. But you might be right. This might be the better way to do it.
I've been happy to see what's happening.
Yeah, I would say for my stuff, one of the biggest changes this year is I'm using AI for a lot of stuff. And if you feed it papers, it's really good. It kind of constrains the hallucinations a little bit. It's yeah, like I'll give it transcripts and I'll give it papers and I'll be like, okay, write something based on what's in this.
Yeah.
And if you give it enough, it can do really great work. And the advantage is, like a lot of people have, myself included, a lot of people struggle with scientific papers. So if you can create a story, it lets them kind of tiptoe into the idea.
Mm-hmm. Mm-hmm.
So.
Yeah, hopefully we can get some good things happening.
Yeah. Joel, you were talking about twisting. You were talking about Heim theory and torsion, right?
Heim twisting? Yes. What is that? What is that? I've never heard of this. Tell me.
I'm not sure if you're aware. I'm working in the framework of Burkhard Heim, who was a German physicist living from the. So he worked from 1940s to 2001, quite under the radar of most people and outside of the academic system, which kind of banished him early on because his ideas were way too big and too fast for the time, and maybe still are. But I was very interested in your presentation, especially. I watched your last presentation as well, and today I understood a little bit more about it. And I also had a talk with Daniel Davis about your work, and it convinced me that I need to have another deep look at your 180-page document, which is quite time-consuming to really get into, right? But definitely, I think it's going to be worth the time.
Do you have any? Do you have any material by time that I could look at?
Yes, I definitely could send you some. We get some English translations now, so
yeah.
The main work is in German, so that was the problem for a long time. It was only in a very complicated German language. And didactically very poor written up, but we're getting some English translations now, so that's I will definitely, and we should get in contact sometime, because I think so one of my main questions would be, everything in your theory is based on smooth manifolds, right?
Yeah, smooth bundles.
Smooth bundles, yes, okay. Yeah. Because like the one of the main things in Heim theory, in which really, oh, did she just drop? Think so, right?
Oh, yeah. Okay,
Yeah.
there. She just re-entered.
Ah,
Yeah.
okay.
Oops. Hold
I
on.
actually left.
There we go.
Smooth
Okay.
bundles is the last thing I said, and that's the last thing I heard. I'm so
Okay,
sorry.
yeah, no problem. Yeah, so one of the main things this Burkhard Heim did is take the quantization to the maximum. He quantized everything, even his base space, right? So he has a metron, is called the metron. It is just the smallest surface area, and that's where everything happens on. So his framework works in 6, later 8 and 12 dimensions, and it's based on a metron lattice. So meaning that you have a smallest surface area connecting all of this. Each dimension with each dimension has a metron that is like the cross surface on which stuff happens. And so I'm also like I'm developing the idea to look if what you're doing is kind of a smooth limit, and if you could, especially because you also get a mass spectrum, right, from his works, and you're getting a mass spectrum.
Yeah,
That's very fascinating.
it
So
is
I want to
fascinating.
do some comparing of the integers in the formulas,
Mhm.
and I have some other ideas about how to compare and study both frameworks.
Very
And
interesting.
see if you can enrich one another, if there are already some
But
I
there's
think that they're
my
quite
theory.
different actually.
Right,
So which is even more exciting. It is not just
yeah,
the same theory. They are two very different theories, and I think
right.
there's a possibility to learn from each other for it.
Yeah, that is exciting. And my theory has a discrete level because there are discrete patterns that come off of uh, um, rotations and other aspects. So, like, it would be interesting to see if what he's getting could be compared to what I'm getting, and if, like, maybe they reduce to one another in some way.
Yes, that's one of the questions. But
Yeah.
so from my intuition right now, I do think that they are very they have
Different?
a very different background mathematically from where they originate. So I
Yeah.
think that you cannot just convert them into each other, but
Right.
that they have to stand for their own. But that's even more exciting because then you have
Yeah.
two theories, not just one theory, which has two
Yeah.
expressions, right?
Yeah.
So
Yeah.
yes, but we definitely we have to get in touch in a real talk, and I might write something up first, and you can read a little bit upon it, and we need to talk further on it.
For
But yeah, it
sure.
was a very great presentation, even though the audio cut out a little bit sometimes,
Yeah.
but no problem.
Yeah, I'm sorry about that. I think I have a solution for the next time if this happens.
And I also have to say, I think it's very exciting stuff with all the presentations today and over the last months. We are getting some real theoretical breakthroughs, or at least people claiming to have them. And of course, if people claim that, they have to back it up with something. But to me, it looks, yeah, Mark, you're pointing at it. We are really trying to back it up directly, and this is what's so amazing about APEC, right? Having the connections to people like Mark and other labs here that actually,
What's
like
the name of the
in
snow
real
globe?
time, try to prove or disprove your claims, which is exactly how physics should be done, and I'm loving it. Great.
It's wonderful. Okay, gang.
Tim,
I'm gonna take off because I'm.
snow globe?
What?
What? Sorry, Mark. What?
Tim, what's the name of the snow globe again?
The eigenglobe.
Scalar snow globe.
Or the scalar scope globe. The scalar eigenglobe.
The scalar snow globe. The eigen mode, by the way, Jenny, is all of the possible resonances.
Yeah, the eigenglobe.
Eigen globe. Oh, that's a cool idea.
But
The scalar
that's almost German.
eigenglobe.
What's globe in German? Joel knows. What's globe in German?
Globus.
Eigenglobos. There you
Der
go.
Eigenglobus.
Eigenglobus.
That's great. Yeah.
I'm gonna print out a label and put it on right now. Scalar
Awesome.
Eigenglobus.
Das scalar.
Der Skalare. Scalar in German is Skalare.
Escalada,
I was doing some research about going to like the AIAA conference or some of the more traditional conferences, but then I realized if they ever see what we do here, they'll never let me in. So
we're too
I'm
cool for
stuck.
school. We're too cool for school.
That's one way to describe it. That's one way to, yeah. That's not how they would describe it, but that's one way.
That's okay. Okay, I gotta get out of here because they're gonna kick me out of this room. But take care,
Okay,
gang.
well, Jenny, thank you so much for presenting. I mean it.
Thank
That's
you.
so cool.
All right, take care. I'll see you soon.
Bye.
Probably next week.
Okay, well, yeah, again, I mean, we've done lab updates. We can just do open discussion if you guys want, whatever you guys want to discuss. It's only 3:30. It's a little slow because it's November. I think that's part of it. But, and actually, I have a lot of folks who want to present stuff like staggered out through December and then January. And then my podcast channel, I'm scheduling myself into oblivion there too. But
Got any cool coming on your podcast?
well, here, let me put Ioannis on. Let me put Ioannis back on. And Curtis is here. He may be hiding though. His camera's off. I don't know if Curtis has an update or not. But
So maybe I have a logistical question. There is a calendar on the website, right? Because I wanted to ask if
there
there
was
is
a calendar on the website. I took that down because it had
Ah.
links and people were using it to spam. So yeah, now, so our next one, let me look. I will take a look now. I don't have a great solution for that because again, people were using that as this tool to spam us.
Okay, that's bad. But it would be really great to have a visual thing to see all the upcoming dates, right? You have the conference, you have open mic, then there's also the other group.
So
And all these dates in advance would be nice to have in an overview.
okay, so let me see. Our next open mic is next week. So Saturday, December 6th is open mic. That's at 4 p.m. Pacific. And then on December 20th, that is the webinar. So December 20th is our next webinar. And I have, in fact, if you'd like, I can bring up, I'm not going to share it on the screen because it has emails and stuff, but let me see, APEC conference presentations. This is always really tentative. I had 2 folks change this week, which is totally cool. But so again, Robert Francis Jr. has been like diligently digging in to the Boyd Bushman magnet drop tests. And he actually, the challenge he ran into was he is using a 30 frame camera, but he has access to a 120 frame camera, but he just couldn't get that ready in time. So we had to bump that back. So I'm hoping that he can present on December 20th. I'm going to write a note in there. And then Hugh Deasy and I have been playing video tag. I think he's got his sound and stuff fixed. I tried to connect with him last night. I will try again this evening. So that is also a possibility. Oops. Okay, and then let me see. So Ron Evans. Oh, and I think Ron is actually pushing back later. So that might be early spring. I have to check on that. Curtis has a unified field theory. And I'm really excited about that because Curtis has dug really deep in several different areas. And so the challenge for him has just, it's a lot to work with and he's juggling a bunch right now. So hopefully December 20th for Curtis. Then Orestes Lazanakis has isotope tests for ET samples. And then Nathan Innan has quantum linearized general relativity and its applications to propulsion. And so that's December. And then in January, Giovanni Cambria has negative energy and Casimir plate experiments. George Egley has LENR gravity and fundamental physics. And Larry Davenport has his overdue TT Flamejet anniversary presentation. So, and I'll put Haslenbach on here as well. Let's see, January, hopefully.
Drew, somebody has a question about stacking layers. If there's diminishing returns or it just adds up.
Okay. Stacking is the, I don't know if y'all ever saw the great chart. See the trough of sorrow? This is the design and manufacturing chart of horribleness. Okay? Let's see. I'm down here in the trough of sorrow. This is where stacking lives. When I first started stacking thrusters, they were 6 inches apart, and they worked great. Then I put them close to each other, and they killed each other. Then I spent 5 years figuring out why they killed each other. And now I have them at 0 stack thickness, so they're literally direct contact, and they're back to making the same amount of thrust they were making back when they were 6 inches apart. So, yes, bringing them anywhere near each other is a very, very bad thing and puts you in the trough of sorrow where you live for many years of unhappiness. So that's the answer to that.
That was important enough to laminate it. Thanks for sharing.
Yes, everyone should have this in their work area. This is it. Experimenting and pivoting and then it starts working. Well, this is like a logarithmic line here, okay? This is years of sorrow. The trough of sorrow is years of general misery. So, hope I answered your question. To find out exactly how to stack them, you show up here in sunny Florida, join the team, sign the NDA, and contribute to the overall awesomeness.
I'd like to hear John.
Excuse me?
Oh, sorry.
Hey, Curtis.
I was thrown in. I didn't know I was unmuted. Go ahead.
John wants a large number hypothesis talk. So, Tim, that's for you, I guess.
The large number hypothesis.
Yeah, that's from John Brandenburg. Todd Desiato is asking, hey, Todd, welcome back. Long time. What has really been accomplished in 2025? That's a good question. I got my the Alzafon setup, got a lot more complex. And we saw some results similar to the X-band in S-band. And we're working towards making a triplet state system with helium cooling. I removed the vacuum system and moved toward a helium recycling chiller system. The setup got a lot more complex, and we're moving away from metals for now and just doing dielectrics.
You know, I'm going to send Mr. Brandenburg and Mr. Desiato a link. Studio link. There. Okay.
So
yeah,
sorry,
there,
you were saying?
Somebody talking to me?
Yeah, did I interrupt you, Drew?
Oh no, I was just looking at the comments here. It says somebody's like in their 8th year of doing whatever it is they're doing. I'm in my 23rd.
I should, Ioannis, you can jump in anytime. Also, for open discussion, it's just open discussion. We try to not interrupt too much, but go for it, man.
Yes, no problem. Okay, if I need to, we'll do it. It's okay. Thank you.
Okay. Yeah. And
actually,
let me see. Todd said he can't make it, but that's okay.
Tim, I just want to mention something. I listened to all this theoretical. And I won't use the word babble because I know that pisses off good people. But I listened to all this theoretical talk and discussion and all this stuff. Okay, what is somebody ever going to be able to take out a piece of paper and draw me a sketch and say, "Hey, could you build this?" Because if you build this thing, it has a shot at working. Okay, until you can actually do something with all of this wonderful theory. Somebody explain to me again what's the point of it?
I think, Drew, I think it's a mixture. I mean, you have some folks that are just doing theory and they're not even looking at applied theory. And then you have other folks that are kind of like, okay, I have an idea. How do we apply this? And so I totally identify with what you're saying. I think it's like stages. Some people start with theory and they're approaching it from that. And then there are other people who like with yourself and Charlie Bueller, right? Like you guys really started with the effect and you're like, hey, we have something. Let's figure out the theory behind it. So
if I may contribute to this.
Go ahead.
Yeah.
In my presentation, I was explaining exactly this. We are in the technological phase of achieving gravitational control, gravity control technology. So if you're interested, look at my articles and presentations, especially on ROCAM, Romanian Conference on Advanced Materials, where I explain what research needs to be done to build two-dimensional materials which are anisotropic in gravitational fields. So the theory is clear. So is this you were talking about?
I already got stuff that can free float. So how do we get to the next stage? I need somebody to build me a warp bubble thing.
No,
I got the impulse engine. I just
if you have the material which floats, then we build the UFOs and we don't warp to a different star, but we colonize the solar system. So that's the next step.
Yeah, I know. I got that part beat. How do you do y'all are talking about this warp bubbles and gravity bubbles and all that other nonsense.
We're talking about a new transportation technology, which is based on anti-gravity controlling gravity, and that's what it needs. The warp bubble, that's yet far away.
You say controlling
about quantum tunnel, not quantum tunnel, but
a propulsion system simply provides acceleration.
No, that's where you don't understand the gravity, because if you reverse the direction of the spin, that you're pulled towards other sources of gravity. So you travel for free. You don't need inertia. You don't need to expel anything. So
yeah, what happens if you're far away from the Earth? What if you're sitting out in the middle of nowhere and there's nothing to push off of?
It's the rest of the galaxies. You fall towards the rest of the galaxy. How is it not clear?
Because it's not. You're
okay.
1 over r squared makes it a long way away from the nearest rest of the galaxy piece of that good stuff.
We have all the other planets. It's like, okay, so.
Yeah, you also have 1 over r squared.
Yeah, I think what you're pointing out to is something
you're not attracted by Earth. You're attracted by Sun. You're attracted by Jupiter. You go wherever you want. It's like skiing on a gravitational.
The gravitational effect of Jupiter on a spaceship would be like the weight of a gnat. So Jupiter ain't pulling you nowhere.
And you are repelling from Earth at the beginning.
Okay, so let's say you get away from Earth, and you're still way away from Jupiter.
And you are repelling
push
from
off of nothing?
You're reversing the direction of gravity. So,
well, what Lucian is talking about is in the Alzafon theory, it's possible to increase gravity as well as decrease gravity. So if you if you resonate the craft in a way that it increases gravity on one side and decreases it on the other, you'll get pulled toward whatever is there on the other side.
What if there's nothing there to get pulled towards?
There's always something there.
Yeah.
But it might just be farther away, and then you have to crank it up a bit. Somebody was asking about Tom Vallone not having a real degree. I haven't graduated high school. His books are great. Buy Tom Vallone's books. That really does not qualify or disqualify anyone from knowing what they're talking about in here. Drew, did you go to school for anti-gravity research or warp drives?
No, I did not. But I read that Vallone guy stuff. I like his stuff. Yeah.
They don't even have school for that. There is no school.
That's my point. There is no school for this stuff.
I got to tell you, the second half of my team, Dr. Charles, is about as sharp as they come. Okay, Literally, he's
And
got
he has
every
all the degrees.
credential you've ever heard of. Literally, he's published everything, and he's got missions on the moon right now, and there is nothing that comes out of his mouth that's useful to building anything. I mean, don't get me wrong. He's set up the physics and he's got equations and all this other stuff. And this is the running argument I have with him for 8 or 9 years now. There's never anything that comes out of his mouth that's useful to me. It just drives me crazy.
Yeah,
So I think you
spent a lot of time in college.
He did.
Drew, I think your question.
College. I've got degrees in aerospace and space propulsion. They're freaking worthless.
I think your question really mixes in with the question from chat. What was really achieved in 2025, right? So the question can be interpreted as, can you really show us something physical now? Where's the real prize that maybe a lot of people really thought that this year would be a breakthrough year? And I think on the theoretical side, it has really been a breakthrough year. There was a lot of really good minds have come together. A lot of really good papers have been written or aren't being written right now, right, Curtis? Hopefully soon to be seen for everybody. And like tools have been built. For example, the Warp Factory tool in which you can plot and work on metrics and stuff. So I think really a lot has come together this year, and the direct translation into something real might take some more years, but the groundwork is laid down here. Was too small to read it, Drew. What was written there?
2.67, 2.63 times Earth unity. That means I have pumped enough magic into a piece of plastic to make it lift 2.6 times its own body weight.
Yes,
I think
exactly.
That's a pretty good thing.
So that's an amazing thing, and what you're doing is so in my point of view, that is the real novel propulsion system that has come out this year, right? But at some point, I think we all want to go a step even beyond that kind of technology. We want to go to a real warp drive
so do
propulsion
I.
system.
We shall hurry up and figure it out.
Well, so actually,
it takes time, but we did some really good steps this year.
If I could redirect for just a sec, Drew, I wanted to ask, you sent me some photos. You were trying to get one that would lift off vertically, and I remember in the photos you'd said that it was your plate was not, it wasn't strong enough, so it was kind of draping. Have you thought about hanging it and doing a deflection test?
I did.
Oh, okay.
It generated the same. That's basically what I do when I do a horizontal pendulum.
Yeah.
I just take the hanging thing and hook it directly to a load cell.
Do you have video of that you could put up for us?
I have video of that, and no, I cannot put it up for you.
Okay.
Yeah, but what he's saying is it's attached to a load cell, so it's not a visual movement. It's just squiggly lines on a screen.
Okay. The movement would be cool, but that's just
everybody says that, but it's the problem is that the system that's inside the chamber weighs about 1 kilogram. It's got the power supply and the frame and all the stuff that's already in there in order to make the magic happen. And then the individual plates weigh about 1 gram, 1.5 grams, something like that, 2 grams. But you got to have all that other crap in there in order to make the thing work. Well, by the time you do the math, the thing's only, whatever it is, it's only 12 inches long. So you do the math in the small angle theory, and it works out to be about 1/3 of a millimeter of travel, maybe 0.5 millimeter. It's real tough and difficult to look at something that takes about 100,000 seconds to move 1/3 of a millimeter. It's a real tricky thing to show.
Yeah. It's what you're doing is it's more complex than it looks.
Right.
It
That's
can be
why
deceptive.
I went to open air testing. So now I can put my stack of thrusters on the little scale and press the button, zero the scale, and watch it pull upwards.
So one thing I should point out,
What's the last time you saw something pull upwards on a scale?
Yeah, one thing I want to point out to folks watching is the reason that you're able to do open air and have it work fairly well is because you've dropped your voltages way down. And so other people have struggled, right? Because I've worked with lifters and stuff like that. When you're running them at like 30,000 volts or something, 25, 30,000 volts, you've got ion flow everywhere. So in your case, you have dropped your voltages way down below the point where you get a lot of ion effects. So
right. Air breaks down in general around 3,000 volts, 3,500, something in that zone. If you have a sharp object at about 3,500 volts, you're going to see, you turn the lights out, you're going to see little purple streamers coming off of it. You get it anywhere near ground, it'll start ozoning and you know, sinking the room up. I operate somewhere around 5,000 volts now, and I'm at about 2 orders of magnitude above the breakdown of air. So I'm still operating at a ridiculously high breakdown field, well above air. But, you know, I've chased that gremlin for years, and I can now run an open air stack that pulls against gravity. But the one thing I want to mention is not only do you have to come up with a way to make a test work, you know, you like dream a test up, and then you build a test, and then you do whatever it takes to get the test to work, and then you figure out a way to demonstrate the test, but you rapidly run into the other side of the real world, and that is manufacturability. I know everybody has heard of TRL, Technical Readiness Level. Hopefully you've heard of Technical Readiness Level. If you haven't, go look it up at NASA. But there's also Manufacturing Readiness Level, MRL. And when you run your test and you actually make something work, your MRL is usually like 1, which is, I just took a piece of paper out and I've listed all of the problems it's going to be to make the thing. And to go from 1 to 2, that thing's a logarithmic scale. It is insanely difficult to get to MRL level 4 or 5, which is I have a real plan on how I'm going to make 1,000 of whatever these things are. I don't know how to do it yet, but I have a real plan. That's what I've been spending this last year doing, is getting my MRL level up to about 5, which is about the TRL level of my hardware.
yeah, there's a ton going on right now. There's a ton, experimental and then theoretical research, and again, my bent is like I love using AI to dig through it, because I feel like as that gets better and better, we're finding hidden gems, you know. So there's a lot going on right now. Well, guys, I think we're at the top of the hour. It's just about 4. I mean, we could keep going for a while, or we could close things down for today if you want. It's up to you guys.
I'm going to cut out, Tim.
Okay.
It's been great.
Should we wrap up shop for the day then, gentlemen?
If Curtis is not coming back to give an update on his paper, I don't know. I wanted to ask him when it's coming out now, but
so Curtis is going to be doing next month. It'll be next month.
He's going to present next month, so yeah, the paper should be out in the meantime. I'm really looking forward to that. Okay.
Well, guys, thank you all. Give yourselves an enormous hand. This has been one heck of an event. Thank you so much. So yeah, I'm going to take everybody out, and this has been APEC for November 29th, 2025, and we have another one coming up on December 20th. If you attend, if you're on our email mailing list, we have an open mic, which is kind of the open discussion that's not recorded, that is coming up next Saturday at 4 p.m. Pacific time. But for the structured APEC that we have right now, December 20th is the next one. That is the next StreamYard version. I want to thank everybody for joining us. Thank you to our presenters for amazing breakthrough frontier science. I am super, super excited. 2025 has been one heck of a year, and it just keeps getting better and better.